হ্যালো, হ্যালো। আপনার দিনে ভিড়টা আর সাউন্ডটা মিউট করে দেন তাহলে ভিডিওটাতে নিচের দিকে দেখুন একদিকে ভিডিওতে একটা মাইক্রোফোন আছে ভিডিওটা অফ করে দেন এইটা মানে দেখুন এবার ঠিক আছে বাম পাশে মাইক্রোফোনটা অফ করে দেন এইটা
Please off your camera. Sir, please off your camera.
Participants are requested to mute yourself and please don't share your screen. Dear participants, we shall start our webinar after 10 minutes, that is sharp 2:30 p.m. Dear participants, we shall start our webinar after 5 minutes. That is sharp 2:30 p.m. Please mute yourself and don't share your screen.
হ্যালো শাহনজ এসছো? শাহনজ তো শাহনজ এখন আসেনি।
হ্যালো স্যার, আমি আছি, বলুন।
ও না, ঠিক আছে, তোমার 2:30টায় শুরু হবে তো? ঠিক,
হ্যাঁ স্যার, 2:30 স্যার।
আচ্ছা আচ্ছা।
ওকে স্যার।
সব স্পিকাররা এসছেন?
স্পিকাররা ফার্স্ট স্পিকার 5 মিনিট আগে জয়েন করবে বলেছেন, আর সেকেন্ড স্পিকার গুলো এসে যাবে। আর আমাদের সত্যবাসী স্যার এসছেন, উনি জয়েন করে আছেন।
পরপর যারা আছেন সেই রকম ভাবে সেই হিসাব অনুযায়ী তারা জয়েন করেছেন কিনা আগে দেখে নিও।
হ্যাঁ হ্যাঁ,
দেখে নিয়ে শুরু
আচ্ছা,
করুন।
তনুকা ম্যাডাম জয়েন করেছেন। ঠিক আছে স্যার, ঠিক আছে।
ঠিক আছে।
Hello, Shahnuz. Hello. Shahnuz. Hello, Shahnuz. Hello, Shahnuz.
হ্যালো ম্যাডাম। হ্যালো হ্যালো ম্যাডাম।
Hello. হ্যাঁ, শুনতে পাচ্ছো?
হ্যালো ম্যাডাম।
হ্যাঁ, শুনতে
হ্যাঁ
পাচ্ছো?
পাচ্ছি ম্যাডাম। হ্যাঁ পাচ্ছি ম্যাডাম, বলুন। ম্যাডাম
শুনতে পাচ্ছো?
ম্যাডাম, হ্যাঁ আপনার সাউন্ড কেটে কেটে যাচ্ছে ম্যাডাম, আপনার সাউন্ড কেটে কেটে যাচ্ছে।
হ্যালো।
ম্যাডাম, আপনার কথা শোনা যাচ্ছে কিন্তু আওয়াজ কেটে কেটে যাচ্ছে।
Hello. Hello, can you hear me?
মমিতা ম্যাডাম, একটু ক্যামেরাটা ঠিক করে নেবেন।
ম্যাডাম আরেকবার লিভ করে আপনি আরেকবার জয়েন করুন। আপনি গুগল মিটটা একবার লিভ করে আরেকবার জয়েন করুন।
আমাকে বলছেন? হ্যালো?
না, আমি আপনাকে বলছি না, ম্যাডামকে বলছি, প্রিন্সিপাল ম্যাডামকে বলছি। ইয়েস স্যার, উই ক্যান হিয়ার ইউ। থ্যাংক ইউ।
পাচ্ছো?
ম্যাডাম, স্বাগতম ম্যাডাম, বলছি আপনার ভয়েসটা কেটে যাচ্ছে, আপনি একবার গুগল মিটটা বেরিয়ে আর একবার জয়েন করুন।
শাহনুজ, শুনতে পাচ্ছো? আমি একটা আওয়াজ করানি, আমি পাচ্ছি না।
হ্যালো ম্যাডাম, শুনতে পাচ্ছেন?
হ্যালো।
হ্যালো ম্যাডাম। হ্যালো ম্যাডাম, আপনি একবার লিভ করে আবার জয়েন করুন, আপনার সাউন্ডটা শোনা যাচ্ছে না।
স্যার নিত্য স্যার কি আছেন অনলাইনে?
হ্যাঁ, আছি।
আপনি তাহলে একটু ম্যাডামকে একবার রিমুভ করুন, ম্যাডাম আবার জয়েন হবে। ম্যাডাম শুনতে পাচ্ছে না হয়তো।
আচ্ছা,
আমি কি শুরু করবো প্রোগ্রাম? হ্যালো, good afternoon everyone. Now we are at the very beginning of our webinar. Life is a mathematical equation. In order to gain the most, you have to know how to convert negative into positive. On the behalf of Chagda College, Nodia, West Bengal, India, I, Momita Pal, the moderator of the webinar, extend a very warm welcome to our patron-in-chief, Dr. Shagota Das Mohanto, Honorable Principal, Chagda College, West Bengal, India, Patron Dr. Ashok Kumar Das, Honorable Principal, Ashannagar MMT College, Nodia, West Bengal, India. Chief guest, Dr. Partho Kormakar, WBES, Deputy Secretary Academic, West Bengal Board of Secondary Education, Government of West Bengal, India. All of our eminent speakers, Dr. Satyabati Shor, Professor Adebayo Agunbaide, Dr. Muhammad Ali Zinna, Professor Tonuka Chattopadhyay. All the members of our organizing committee, convener Dr. Shahanush Mollik, Assistant Professor and HOD, Department of Mathematics, Chagda College, co-convener Dr. Nitya Gopal Bishwas, Assistant Professor, Department of Mathematics, Chagda College. All the guests across the globe connected with us through the live webcast. We are extremely thrilled to see such a large number of viewers connected across the globe in order to participate in the 2 days international webinar on recent advancements in mathematical sciences and its applications, organized by Department of Mathematics, Chagda College in collaboration with Ashannagar MMT College. Today is the first day of our webinar. I thank all the viewers for such active participation. We had massive responses, over 700 participants from over several organizations across the globe. Almost every state of our country and many other countries except India like Pakistan, Nigeria, Cameroon, Bangladesh, Philippines, Morocco, and United Kingdom. All the participants are requested to keep your microphone option in mute and video option in off mode. And all the participants are also requested not to click on the present button on the Google Meet screen during the webinar. I may now request Dr. Shagota Das Mohanto, Honorable Principal, Chagda College, to give welcome address.
নমস্কার, শুভ মধ্যাহ্ন। Today is a remarkable day because this is the first time Department of Mathematics, Chagda College, in collaboration with Ashannagar Madan Mohan Tarkalankar College, is going to arrange a international level webinar on mathematics. We are very much proud that the principal of Ashannagar Madan Mohan Tarkalankar College extended his helping hand, cooperate us seriously and cordially to arrange this webinar. Thank you and most welcome Dr. Ashok Kumar Das, Principal of Ashannagar College. Ashok da, আপনাকে শুভেচ্ছা এবং ধন্যবাদ জানাই, স্বাগত জানাই। Today we have with us eminent speakers like Dr. Partho Kormakar, Deputy Secretary Academic, West Bengal Board of Secondary Education. We have with us Professor Bao Aguinbiel. May this pronunciation is not right because of our Indian language, I think. Department of Statistics, Olabisi Onabanjia University, Nigeria. We have with us Professor Tonuka Chattopadhyay, Department of Applied Mathematics, Calcutta University, and Acting Dean of Science. And we have with us today Dr. Shottobachi Shaw, retired professor, Department of Mathematics, MBB College, Agartala, Tripura, India. This is the first day of our international level webinar. On the second day, we will have to place another 3 or 4 eminent speakers, resource persons. We must welcome all the participants, all teaching and non-teaching members of our college. We must congratulate the effort that had been taken by our department, by the faculty of mathematics department, and as well as other department of my college. I must thank and I must welcome to all the participants and students also. Now, as there are many speakers, many eminent resource persons, and I know little on mathematics, about mathematics, so I have to stop now, and the eminent speakers will take the session. They must help and enrich our participants. I hope this seminar, this webinar will be a grand success and will be a remarkable landmark in our for our Chatta College. Now, listen to them. আবারও স্বাগত জানাচ্ছি, ধন্যবাদ জানাচ্ছি উপস্থিত সকলকে। এই প্যান্ডেমিক সিচুয়েশনেও এই ধরনের ওয়েবিনারের মাধ্যমে আমাদের সারস্বত চর্চাকে বজায় রাখার জন্য এই লড়াইটাই আগামী দিনে ইতিহাস হয়ে থাকবে। ধন্যবাদ, নমস্কার।
Thank you, ma'am, for your valuable speech. I humbly request Dr. Ashok Kumar Das, Honorable Principal, Ashannagar MMT College, to give inaugural speech.
Sir, please unmute, sir.
শোনা ওখান থেকে সরে যাতে শোনা, ছবিটা চলে যা, পরে করিস। হ্যালো, I am audible?
Audible, sir, audible.
Yes, sir.
Visible, not visible. Now visible. Hello?
Yes, sir, you are visible and audible also.
Okay. Good afternoon to everybody. I'm very much delighted to join this international webinar on mathematics as a collaborator. I'm grateful to the authority of Chakda College for offering us for this collaboration. Now, on behalf of Ashannagar MMT College, I, the principal of this college, I'm delighted to welcome to all eminent resource persons. Here, our chief guest, my beloved friend, Dr. Partho Kormokar, WBES Deputy Secretary, Academic, West Bengal Board of Secondary Education, and there are so many resource persons. Today, we have with us Dr. Shottobachi Sir, ex-professor, Department of Mathematics, MMB College, Agartala, Tripura. Dr. Abedia Agunbiad, Professor in Statistics, Department of Math, Olabisi Biano University, Nigeria. Dr. Tonuka Chattopadhyay, Professor, Faculty of Dean and in Applied Mathematics, University of Calcutta. I congrats to the all staff of the Chakda College for their active involvement in this program. I also welcome to our viewers who have joined this international webinar on Google Meet and YouTube. I do believe that this 2-day program will fulfill our expectation of knowledge. I also congrats Dr. Shahanaz Mullik and his fellow who have hard worked to conduct this program. I also say something. I do believe that mathematics has own language, but it has no limitation and it has no limited area in our world. Now mathematics is taking entry in all area in different way and different field. So I think mathematics is going in advance in all round. Let us start our program. I convey my gratitude to all the resource persons who have joined this program. Thank you to everybody.
Thank you, sir.
কথা শোনা যাচ্ছে না।
Momita, please open your mic.
একদম টেপাটেপি করবি না, শুনলে ভালো হয়।
Momita, please open your microphone. On your microphone.
Okay, sir. Thank you, sir, for your valuable speech. Our chief guest, Dr. Partha Karmakar, Deputy Secretary, Academic of West Bengal Board of Secondary Education, has served so many important posts like OSD and ex-officio Assistant Director of Public Instruction, Education Directorate, Government of West Bengal, Bikash Bhavan, Kolkata, Office in Charge, Muragacha Government College, Nodia, Faculty Member of Bethune College, Kolkata, Jalpaiguri Government Engineering College, Jhalda, and AM College. Now, I humbly request Dr. Partha Karmakar to give keynote address. Sir, you may proceed now. Sir, please unmute yourself. Sir, please unmute yourself. Partha sir, please unmute yourself. You are not audible now. Sir, please unmute yourself.
হ্যাঁ স্যার ট্রাই করছি।
Hello, am I
Yes, sir,
audible?
you are audible now. Yes, sir, you are audible. Yes, sir, you are audible now.
Namaskar.
Please continue.
Okay.
Yes.
Okay. Namaskar. Good afternoon to all of you. We have assembled virtually to celebrate recent advancements in mathematical sciences and its application for 2 consecutive days on this webinar platform. I strongly believe that this webinar will put light on different corners of mathematical sciences. I am feeling proud to have Dr. Sagota Das Mohanto, Honorable Principal of Chakda College, Dr. Ashok Kumar Das, Honorable Principal of Ashan Nagar Madan Mohan Tadkalankar College, and Dr. Shahanaz Mullik, Assistant Professor of Mathematics and convener of this webinar. All dignified participants and delegates who will listen the valuable talks of such renowned speakers on this webinar organized by Department of Mathematics, Sagda College, which is affiliated under University of Calcutta, University of Kollani, West Bengal. I am privileged to pay due respects in keynote address to the speakers of today's seminar, Dr. Adebayo Agun Biade from Olabisi Olabanjo University, Nigeria, Dr. Muhammad Ali Jinnah, Aizar, Kolkata, Professor Tonuka Chattopadhyay, Department of Mathematics, University of Calcutta, and Dr. Satyabachi Shor, renowned mathematician and ex-professor of MMB College, Tripura, will enlighten us with their discussion in today's topic. Mathematics is the mother of all subjects, a century-old proverb, and it is true in all aspects. In today's situation, life without the application of mathematics can never be imagined. Any sort of utilities of today's livelihood depend directly or indirectly on mathematics and its vast range of applications. That is why our ancient old tradition of doing mathematics or practicing mathematics and dealing with its inherited beauty is going on through the ages in pure as well as applied versions. To the mathematics lovers who try to understand and live with this beautiful subject in India, this subject has two branches. One is called pure mathematics and the other is called applied mathematics. Broadly speaking, this subject is an institution itself and it has two major departments, pure and applied. Mathematics in life can be gently compared with the importance of salt in food industry. We know that without salt, food has no taste. For taste authentication, its measured appreciation is highly with the presence of mathematics. Mathematics is the core of this subject and it leads the foundation stone of it. The key of its part is abstract in nature. We have to give big effort to visualize the essence of it. Common people say that it is dead, but truly speaking, it is lively as it was 3,000 years ago. Still, good research papers are developing on old myths of it. For example, infinitude of times, we know that great mathematician Euclid proved it in 300 BC. But till then, lot of works have been done on it and around 400 independent proofs are there on it. Mathematicians like Gauss, Kumar and Einstein worked on it and developed new proofs. But this is not the end. In this recent, a paper has been published. All of us know it. In Amir Mathematics Monthly Journal, in the year published in the year 2015, volume number 5, at page 466 by French mathematician Sam not sealed, as a one-line proof of the infinitude of primes. Though in recent years, many other mathematicians find some flaws in the argument of this proof. We are not discussing about its merit or demerits of the paper. Our main focus from this paper is that a century-old theorem with over 400 proofs, and still mathematicians are trying to find out new proofs of it. This is the main what I mean to add. So mathematics never die and even never become old. New research in well-known areas as well as undiscovered areas develop new branches every day. For example, we can think Fermat's last theorem. Andrew Wiles opened up new areas of mathematics in proving this 400 years old number theory problem. Deep concepts in geometry also used here, which was beyond imagination of many eminent mathematicians. In 17th century, mathematicians are dealing with real numbers and its properties. In 19th century onwards, abstract concepts in this field were gradually getting development beyond pure mathematics. Topology came henceforth, but development never stops. Today, we are dealing with fuzzy set theory, fuzzy logic, fuzzy topology, concept of logical statements as either true or false is getting hammered, and a new concept develops. That is, there is something which is neither true nor false. That two states concept are no longer exist in some sense, and that is fuzzy topology, fuzzy algebra make huge opening in today's research. Not only that, graph theory in proving the theorems of abstract algebra, but also a recent trend to visualize the abstract algebra. Visualize. In mathematics, is a very important term, visualize. You have to visualize the subject. So our old versions of studying topology, algebra, geometry, real analysis, complex analysis, measure theory, functional analysis, harmonic analysis is now mixed up. Research in the purest part of these subjects is getting difficult by every day. Mathematicians are now trying to visualize these subjects through one another, and this leads some major breakthrough in the developing new paths and new research areas. Subjects like algebraic topology, algebraic geometry, commutative algebra, commutative algebra, analytic number theory, combinatorial number theory, low dimension topology, hyperbolic geometry, geometric group theory, complex dynamics, etc. are the recent areas where mathematicians are doing their best and trying to develop new goals every day. In different research institutions and universities throughout our country, with their eminent mathematicians and researchers, put huge efforts in development and progress of the subject with the new concepts and results. These are all about the purest version. But common people do not bother with these facts. They want practical implications and applications of those results. Applied mathematics does this. It is application oriented. It took the purest part and applies it to generate results which can really change the human civilization, such as differential equation, It has huge impact in developing subjects like fluid dynamics, like fluid mechanics, even in huge applications in aerospace engineering and cosmology, which is a subject by which or in which human being is trying to get his place in the universe. Optimization theory is a discipline which gets itself only in the time of Second World War. Now, its importance is surprising us to build a nation. Statistics, a branch of applied mathematics, now it becomes a subject itself. Mixed with optimization theory and analysis helps to forecast the economical growth of a nation. Every day, new developments and research in these areas are carrying out to generate new concepts which can be utilized for nation's progress. Another interesting part of applied mathematics is coding theory. Security systems are totally dependent on this subject. It is not only applied part, it is a mixture of applied and pure. Number theory, computational, commutative algebra, etc. are being used hugely by the mathematicians for the development of coding theory. It is new generation and whose prospect is there behind the subject. Lot of mathematicians of pure and applied mathematics spend huge time in research on this topic. Lastly, in this current situation, we all are focusing ourselves in this fact that when will we be back to our normal life? That is a big question. That is a big question. A very big question. Lot of analysis is available in this concept. But without mathematics, it cannot get its proper shape. A very new subject, hardly 50 years ago, helps to do this type of short analysis. Physics and chemistry depend on mathematics. It is known to all. But biology with mathematics was hard to imagine even in 50 years back. In higher state of research at present, interdisciplinary subjects get priority like mathematics with biology forms mathematical biology, commonly known as biomath. Now mathematicians are as accurate as biologists in predicting the nature of biological experiments using their mathematical analysis, differential equations, and mathematical models. Every day, even in newspaper, we are getting many models on COVID-19. But we know that all are the part of mathematical biology. A new subject has huge impact in human race. Vast areas are still open in research and getting astonishing results. We are fortunate enough to get many mathematicians like Ramanujan, Harishchandra, Vardhan, Narasimhan, Seshadri, Raghunathan, Mohan Maharaj, Infos Prize winner, Manjul Bhargav, Fields in the year Fields medalist in the year 2014, Akshay Venkatesh, Fields medalist 2018, and so many mathematicians are there to mention. Their works influence us to do good research in mathematics and help us to understand the trends of mathematics. Now, I want to thank to the principal of this college, Dr. Das Mohanto, and Professor Sahanaj Mollik, and all the teaching faculty members of Mathematics Department and organizing committee of this webinar for inviting me to be here as a keynote speaker. So, and I wish every success of this webinar, of this today's webinar, and I expect all of us will learn a lot from this webinar. Namaskar. Good afternoon to all of you. Namaskar.
Thank you, sir, for your so much informative and interesting speech.
Welcome, welcome, welcome.
Thank you. I now take the privilege to begin the international webinar, Recent Advancement in Mathematical Sciences and its Applications. It is my pleasure to introduce our first honorable speaker, Dr. Muhammad Ali Zinda. Dr. Zinda, presently the Assistant Professor of IISER Kolkata, Department of Mathematics and Statistics, and former Assistant Professor, NISER Bhubaneswar 2017 to 2018, had done his MMath and PhD in Mathematics from Indian Statistical Institute. He did a wonderful work in projective modules and conflict intersection. He had received Inspire Faculty Award from DST in 2016. He has also published several research papers in some reputed journals. Today, he will be delivering a talk on efficient generation of ideals. We are eagerly waiting to listen from him. Viewers are free to ask any doubts or questions to speaker by typing them in the chat box on YouTube and Google Meet. During the session, the organizing committee members may ask their doubts or questions from respective speaker when their session ends. A warm welcome to Dr. Muhammad Ali Zinda. Sir, you may proceed now.
Thank you very much for the invitation. Today I will speak on efficient generation of ideal. So this is basically related to the problem finding the minimal number of generators of an ideal. Okay. So let me start. Is it visible?
Yes, visible.
Fine. So let me start with some notation and convention. So throughout my talk, my rings are always commutative natural ring with identity. And for an ideal I, mu I denotes the minimal number of generators as an R module. Okay. So in general, computing the minimal number of generators is an extremely hard problem, even if you are working in a polynomial ring over a field. So what I mean by that, so suppose K is a field and you consider the polynomial
Sir,
ring.
please present your slides again because it's not visible now.
Oh, okay, sorry. Let me just check.
Close your slides, then again present.
Is it visible now?
No, sir.
Okay, fine. Slide not visible here. Oh, why is that?
Sir, visible, sir, visible.
Okay, fine. Thank you. Okay. So what I was saying that if we have an ideal in a ring, then computing the minimal number of generators of that ideal is an extremely hard problem in general. Even if you are working with a polynomial ring over a field, So suppose we have a field K, and if you consider the polynomial ring over that field, Kx1 to Xm, and if you consider any ideal inside that polynomial ring, then it is also very difficult to find out the minimal number of generators for that ideal I. Okay, so this is a nice result due to Macaulay. So what he did, he considered just the algebraically closed field C and considered the polynomial ring in 3 variables over C. So he proved that if you start with some integer r greater than or equals to 4, then one can construct a prime ideal P of I2. So so this is the technical term. So I2 I still have not defined it. So yeah.
Sir, again your slide not visible.
Oh, okay. So please give me. Let me just check. Okay, let me just change my connection.
Sir, please unmute yourself. Jinna sir, please unmute yourself.
Is it visible?
Yes, visible and audible also. Yes.
Okay. So this is a result due to Macaulay. So what he proved, he considered the field of the field of complex numbers, and he considered the polynomial ring in 3 variables over C, and he proved that if you start with any integer greater than or equals to 4, then one can construct a prime ideal with minimal number of generators is at least 4. So you can see that actually, if you consider the bounds for those prime ideals, so this is unbounded sort of. Okay, but the situation is far better if you further assume that the variety defined by this prime ideal is regular. So what do you mean by that? So the way I have written is very messy, but yeah. So this is not a result by Foster, Sathe, and Mohan Kumar. So we have 3 different results, but I have put it in a single one. Okay. So what they proved that so here we have taken just a polynomial ring, and then one can construct a prime ideal with minimal number of generators is at least that number r. But the situation is for better if we further assume that this prime ideal has a nice property in the following sense, that if you consider the variety defined by this prime ideal, then it is regular. Or in other words, if we consider this polynomial ring Kx1 to Xm, so this is the polynomial ring over that field K, and P is the prime ideal. Now consider the quotient of P. So that means X1 to Xm mod P. You are going modulo P, the quotient ring by P. Then it is a regular ring. In that case, Forster proved that this prime ideal P is generated by at most m plus 1 many elements. So m is the number of variables here. So which is actually the dimension of this ring. Okay. So in this situation, P is generated by at most m plus 1 elements, or mu of P is less than or equals to m plus 1. That's what he proved. So he gave a bound, and this is quite nice. But at the same time, he conjectured, Forster, that actually we can bound it by m, or in other words, mu of P is less than or equals to m. So that was settled by Avinash Sathe and Mohan Kumar. Okay, so initially Sathe considered it for a regular ring containing infinite field, and later, Mohan Kumar generalized it to arbitrary field. Oh, yeah. So this is for infinite field, and Mohan Kumar then generalized it to arbitrary field. Fine. So now let me digress a bit and consider the following observation. So suppose you have a ring R. So ring means here commutative Noetherian ring with identity. And suppose you have an ideal I inside R. Then the minimal number of generators of I mod I square is less than equals to mu of I, which is less than equals to mu of I mod I square plus 1. So basically we are giving a bound for the minimal number of generators of I in terms of the minimal number of generators of I mod I square. Obviously I have not explained why suddenly I have started with this, the minimal number of generators of I mod I square. So for that we need to recall the proof of Foster, Sathi and Mohan Kumar. So I'm not going into that part. So basically, this part is always true. Okay, so let me first consider the lower bound of minimal number of generators of I mod I square. This one is almost immediate, because if mu of I is m, let's say I is generated by a1 to n, then consider the image of those generators inside I mod I square, that will generate I mod I square. So the lower bound is almost automatic. And for that we need a proof. I'll give a proof. Okay. But this bound is not this basically we are interested in this lower bound, right? So the question is when this lower bound attains. Okay. So, but this is not true in general if you consider any Dedekind domain. Okay, and if you consider any non-principal ideal, then in that case the left hand side inequality is strict, or the lower bound need not attain. So okay, let us take one precise example. So consider z of square root of -5. So what is this ring? So this ring is nothing but zx mod x square plus 5, right? This is the quotient ring by x square plus 5. And now you consider this non-principal ideal. So the ideal generated by 2, 1 plus square root of -5. So clearly this is not principal. One can easily check it. So that means what? That means the minimal number of generators of I is 2. Mu of I is 2 here. Now consider I mod I square. Now I mod I square, if you compute I mod I square, then one can see that actually this is generated by the image of 1 plus square root of -5 inside I mod I square. What does it mean? That means mu of I mod I square is actually your 1. So clearly this inequality is strict in this case. Or actually you have some other nice example. If you consider the coordinating of real 3-sphere, in that case the real maximal ideal, if you consider the real maximal ideal, in that case this inequality is strict. Okay. So now the question is when this lower bound attains, or in other words, when is mu of I mod I square the same as mu? Okay. So this is our main concern, this question. Fine. So, okay. Let me just try to give a proof for the upper bound. It's very easy to check. I hope you have learned Nakayama lemma. So this is regarding the finitely generated R module. Okay. So suppose you have a finitely generated R module M and I is an ideal of R, such that you have this relation Im equals to M. Now, since M is an R module, so clearly you can restrict that operation to I and you can talk about Im. So in that case, what happens if you can find out one element from this ideal I, such that 1 minus M equals to 0. And the proof is very much linear algebraic. One can use those determinant and those kind of thing, and one can prove this result. Okay, Nakayama lemma. But this is a very nice and famous result. Now, one immediate consequence is, if you further assume that I is contained in the Jacobson radical. So what is Jacobson radical of a ring? So this is nothing but the intersection of all maximal ideals of that ring. In that case, Im equals to M will imply M equals to 0. Okay, so what you have Im equals to M and I is contained in the Jacobson radical. In that case, M is actually 0. So this is actually the consequence of Nakayama lemma. Fine. Now, so this will give you the upper bound for mu of I, or the proof for that. So suppose I mod I square, then what you can check that I is actually generated by an idempotent element, or in other words, there exists an element A inside that ideal I, such that I is generated by A and A square equals to A. That means A is idempotent. Or in other words, if you have I equals to I, in that case, I is generated by an idempotent element. And the proof is almost trivial. So let me give you a sketch. So one part is almost clear that if you can find out that I, then clearly the ideal generated by A is contained inside I. Oh, I think, let me check the time. Oh, I think, let us skip this proof for timing, because yeah, this one is very trivial, one can check easily. Okay. So yeah, this is the generalization of our previous lemma. So initially we have considered that I equals to I square. So that means this part is 0. Or in other words, I mod I square is generated by those n many elements, A1 bar to An bar, where bar I mean going modulo I square. In that case, we can find out an element inside I such that I is generated by n plus 1 many elements, right? I is generated by A1 to n and that extra element E. And you have some relation between this E and those A1 to An. What is that relation? That E into 1 minus E belongs to that. Okay. So again, you have to use the previous result. So just you going modulo this ideal, then what you have I bar square equals to I bar. Then using the previous result, you can find out one E such that I bar is generated by this, and this E bar is idempotent. Now this will imply I bar is generated by the ideal generated by E. What does it mean? That means I is generated by 1 to n, comma E. That means I is generated by n plus 1 many elements. And the second relation will give you this one. So you are going modulo bar means you are going modulo the ideal generated by 1. So clearly you have this relation. So now let us go back to that bound. So here we want to prove this one. So let us assume that mu of I mod I square is n. That means what? I mod I square is generated by n many elements. So that's what we have here. That I mod I square is generated by 1 to n. In that case, what we have proved, that I is generated by n plus 1 many elements. Right? That means mu of I is less than equals to n plus 1. Maybe it is generated by some lesser number of elements, right? So mu of I is less than equals to n plus 1. Or in other words, mu of I is less than equals to mu of I mod I square plus 1. So we have that upper bound. So that's what we have proved. And obviously we have some extra relation, but yeah, we need it for some examples. Okay. So now let me put this thing as a definition. So an ideal I of a ring is said to be efficiently generated if mu of I mod I square equals to mu of I. Or in other words, an ideal is said to be efficiently generated if the lower bounds are attained. Okay, so this is the definition of an efficiently generated ideal. Okay, so let me consider one example. So suppose you have a local ring. What does it mean by a local ring? So it means that R has exactly one, or R is a unique maximal ideal. It has exactly one maximal ideal M. In that case, every ideal is efficiently generated, or in other words, mu of I mod I square is same as mu of I. So for a local ring, so one example of a local ring. So basically, yeah, field is the trivial case, and then what you can do. So basically, okay, I'm not okay. So you have to localize that some prime ideal, then it will be a local ring in that case. Okay. So yeah. So again, the proof is almost trivial if you so use the Nakayama lemma. So what is almost immediate, right? That this, so already we have proved that mu of I mod I square is less than equals to mu of I. What we have to check that mu of I is less than equals to the mu of I mod I square. So let us start with a set of generators for I mod I square. So by our previous result, what we have, I is generated by n plus 1 many elements with this relation. Now, if so, E is coming from I, right? And since the ring has exactly one maximal ideal M, so clearly I is contained inside M. Obviously, I is not the whole ideal, clearly. And this is the Jacobson radical, because what was the definition for Jacobson radical of a ring? This is the intersection of all maximal ideal. And we are dealing with a local ring. So that means the ring has exactly one maximal ideal. In that case, E is contained inside I, and I is contained inside M. So in particular, E belongs to M. Now this is a nice exercise to check that if E belongs to the Jacobson radical, then 1 minus E is a unit in R. Since E belongs to the Jacobson radical of R, so 1 minus E belongs, so is a unit in R. So if 1 minus E is a unit, you can multiply both sides by 1 minus E inverse, right? In that case, what you have, E belongs to the ideal generated by A1 to N. Or in other words, I is generated by A1 to N. So that will give you the proof. Okay? Yeah.
Sir, sorry, again your slide is not visible, sir. Please, sir, slide.
Oh, sorry. I don't know why.
Sir, actually, it's not your fault, sir.
Okay, so then I'm happy. If it is not my fault, then I'm happy. Okay, so is it okay now?
Yes, sir, it is visible.
Is it visible? Okay. So the next example is the semi-local ring. So first we have started with a ring with a unique maximal ideal. Now I'm saying you start with a ring with finitely many maximal ideal. A ring with finitely many maximal ideal is called semi-local. In that case, every ideal is efficiently generated. Or in other words, if you start with any ideal in this ring, then minimal number of generators of I mod I square is same as minimal number of generators of I. Okay, so I'm not going into the proof because of time. Okay, and this next result is about the polynomial ring. If means the ideals inside the polynomial ring. So suppose you have a local ring. Okay, so that means a ring with a unique maximal ideal M, and you consider the polynomial ring over that ring. In that case, if you have an ideal that contains a monic polynomial, then it must be efficiently generated. So what I'm saying that if your ring is local, and if you consider an ideal inside the polynomial ring over that ring R, which contains a monic polynomial, in that case, the ideal is efficiently generated. Okay, so these are the examples of such rings. Basically, obviously, it depends on the ideals, the properties on the ideals and the rings. So I'm dealing with basically the rings, the properties of the rings. Again, I'm skipping the proof. Okay, and then the next result is about the relation between the height, minimal number of generators of I mod I square, and the dimension of the ring. So it says that if the minimal number of generators of I mod I square is greater than or equal to dimension of R plus 1, then in that case I is efficiently generated. So this is a very famous result due to Kronecker. So what do you mean by dimension? Just you consider the chain prime ideals. Okay. So basically this is the maximal length of such chain. So this is called the dimension. So if mu of I mod I square satisfies this relation, in that case I is efficiently generated. Okay. And now let me consider the famous conjecture due to Pavan Murthy regarding the efficient generation problem. So this is a very famous conjecture. So suppose you have a field K and you consider the polynomial algebra over that field K. Okay, and suppose you have an ideal such that the height of that ideal is same as the minimum number of generators of I mod I square. In that case, the ideal I is efficiently generated. So he made this conjecture in 1976, and still it is open in general. Okay, so suppose you have a field and consider the polynomial over that field K, and you start with an ideal such that the height of the ideal is same as the minimum number of generators of I mod I square. That is, minimum number of generators of I is N, or in other I is efficiently generated. And the best known result to this conjecture is due to Mohan Kumar in 1978. So he proved that if we have some relation between the minimal number of generators of I mod I square and the dimension of R mod I, in that case, I is efficiently generated. Or in other words, he assumed this extra hypothesis and gave an affirmative answer to move this one lecture. And this is the best possible result till now. Okay. So yeah, so this is a very technical sort of hypothesis, but actually it comes from geometry. Okay, that why he suddenly took this relation that mu of I mod I square is greater than equal to dimension of R mod I plus 2. Okay, so basically this is related to the join of two surfaces in geometry. So I'm not going into that part. And then Satyamandal generalized it to arbitrary polynomial ring. So basically he started with a field, right? Now he's started with any commutative natural ring. Okay, and he took the same relation, but he assuming one extra condition that the ideal contains a monic polynomial. But which one is this hypothesis is automatic here? Since we are dealing with a polynomial ring over a field, so one can use Nagata transformation to assume that I contains a monic polynomial. So actually this condition is automatic here. So one can think that yeah, these two hypotheses are essentially same. Okay. Yeah. So basically now we consider this type of ring. So basically we consider the polynomial ring over a field, and then we consider this Ax, Y. So where A is the polynomial ring over that field, and we consider R to be xy mod xy minus x, when f defines a non-singular hypersurface in Kn. So this is very interesting actually. One can easily take that this ring containing lies in between R Ax and Axx inverse. So that means it lies in between the polynomial ring over A and the Laurent polynomial over Ax and Ax inverse. Or in other words, this ring lies in between kt1 to tnx and kt1 tnxx inverse. Okay, now if you consider any finitely generated projective module over this ring, that is k1 t1 to tnx for the left hand side ring, they are finitely generated. If you consider the finitely generated projective module over the right hand side ring, they are finitely generated. But for one Murthy proof that the Grothendieck group of this ring is not even finitely generated, so we have a huge class of finitely generated projective module which are not free. So that's why this ring is interesting. That what happens is that this ring, okay, it lies in between two rings which are very nice. But this one is you can find out such example of such ring that where the finitely generated projective modules are not free. That's why we have considered this ring and considered the efficient generation of ideas. Now, we have proved that if mu of I is equals to the dimension of the ring plus 1, that's already efficiently generated. That case. In that case, we have proved that this is actually efficiently generated. And let us analyze it to arbitrary commutative ring. That if we have a ring between x and x inverse, in that case, the ideals are efficiently generated. Okay, and finally, okay, then we have considered. So why we have considered this ring? So actually, we are replacing f by 0. In that case, you have this ring. Okay, and then we said that yeah, if we consider any angle of height, in that case, actually, it is efficiently generated. And later we observed that this is one of the simplest example of a discrete Hodge algebra. So what is a discrete Hodge algebra? It's basically a polynomial ring modulo a monomial ideals. And it was first considered by Tornvorst, and he considered the finitely generated projective module of such ring, and he proved an analogous result to Serre's conjecture, or the result due to Suslin and Quilling. Okay. So we proved that if you consider a discrete Hodge algebra and an ideal of height, in that case it is actually generated. So I'm always doing so where
Hello?
this is the dimension. Yes.
Jinna sir.
Yeah.
Hello.
So I think
Sir, your slide is not
Yes.
visible.
again. Oh my god. Okay. Anyway, I'll stop within 2-3 minutes. Okay, just I don't know what is happening. So basically, then we have considered is it visible now?
Yes, sir. It is visible now.
Yeah, fine. So then consider our problem or the efficient generation of ideals problem over the discrete algebras. We have proved the case or when the minimal number of letters 5 more the dimension of brain in that case is efficient generated. When the name of parameters is actually I is efficient. But our main concern is actually so tackling this problem, and this is a very conjecture. So I think I should stop. Yeah.
Hello. Sir, can't hear you, sir. Sir?
Yeah.
Can't
Yes.
hear you, sir. Microphone is problem, sir.
So what to do now? Can you? Okay. So let me just check once. There is some. Can you hear me? Can you hear me?
Yes, sir, you are audible now.
Yeah, okay.
Yes,
So if you
sir.
have
Yes, sir.
yeah. So basically, I have finished. I think I should stop because my time is from 3 to 3:30. I think, right?
Yes, sir.
Yeah. So if you have any doubt or query or any question, you can ask me. So that will be better, I think.
I thank Dr. Zinga wholeheartedly for his presentation. Now, we would like to take questions from audiences. First question has come up from Shivraj Swami, and the question is, how many ideals are possible for ring of integers?
Why every okay, sorry?
How many ideals are possible for ring of integers?
I'm not. Can you repeat?
Yes, sir. I am repeating the question. How many ideals are possible for ring of integers?
Okay. So there are basically how many ideals, right? So basically,
How many ideals?
Yeah. So it corresponds to the integers. If you start with an integer n, then there is an ideal corresponds to n. So this is nothing but the ideal generated by n. So basically, there are countably many ideals. Okay. So it corresponds to the integers. And if you are searching for the prime ideals or maximal ideal, then it corresponds to the prime elements of the integers. So there are countably many ideals, or basically the ideals corresponds with the integers inside Z. Okay. So if you start with any n integer, you have a corresponding ideal generated by that element n. Okay. So I think someone has written, Vikram, that why every prime ideal in R is maximal. No. This is not true. So just you consider this ring of integers, that is Z, and you consider 0, the ideal 0 ideal. Okay, in that case, 0 ideal is actually a prime ideal, right? Because if you take the product of two elements, if it is 0, then either means one of them is 0. So 0 ideal inside Z is prime ideal, but this is clearly not maximal because it is contained inside. If you start with any prime element, so 0 is contained inside PZ. Or okay, so take one particular case, that is 2Z. what is the definition of a maximal ideal? So if we have another ideal in between that maximal ideal and Z or the ring, then it is either this ideal or the whole ring. But if you consider 0 ideal and Z, you have ideals, right? 2Z, 3Z, strictly contained inside this 2. So clearly in a ring, there are prime ideals which are not maximal. So one example is Z. If you consider the 0 ideal, this is prime but not maximal. And if you are searching for non-zero, then you consider ZX. So basically, let's say Rx. R is the field of rational number. Yeah. So I think is where R is a finite commutative ring with identity. Okay. In that case, what happens? So if you are dealing with R is a finite commutative ring with unity, that's what you are saying. Okay. Now, if you are dealing with a prime ideal, okay. Now, what is the relation between prime ideal and maximal ideal? So let us start with a prime ideal P. Now going modulo P. So R mod P is an integral domain, right? Since P is a prime ideal, so R mod P is an integral domain. Now every finite integral domains are field. So in particular, R mod P is a field. Now R mod P is a field if and only P is a maximal ideal. So you are done. Obviously, you have to check that for a commutative ring, a finite commutative ring, every integral domain actually a field. That is very easy to check. Okay. So is it okay now, or just consider the alternate definition in terms of quotient ring? Start with a prime ideal, go modulo that. This is an integral domain. Since this is finite, this is the field, and hence it is a maximal ideal. You are done. Yeah. Anything else? I hope Bikram, it is clear to you. Yeah. Okay. Anything else?
We have another question from Shuman Biswas. The question is, what is conjecture?
Okay. So basically a conjecture, you have a question, okay, but you have something in your mind that this is true, sort of. You see, one can ask a question, right? But also you have some feeling for that it might be true, or you have something in your mind. So a question with a, let's say, positive sign, sort of. Okay. So you can so let us put it as a question. Okay. But he believes that actually this conjecture is true, but he doesn't have any proof, sort of. Okay, so that's what his feeling or her feeling. So when someone is asking something and if he or she believes that it might be true, in that case we call it a conjecture. So basically, this is nothing but with some feeling. That's all. Yeah.
Yes, sir. We have another question from Shivraj Swami also. How to find the maximum ideal of any ring?
Okay, any ring. No.
With an example, huh? Yes. How to find maximum ideals of any ring with an example?
Okay. No, in general, that is a very difficult question. That how to consider all the maximal ideals. But what you can do, if your ring is a bit nice, for example, consider just a ring of integers that is Z. Okay, in that case, you can find out all the maximal ideals. So in that case, maximal ideal. So okay, I think you have learned that if you are dealing with a PID or Euclidean domain, in that case, what we have, if you consider the ideals generated by irreducible elements, that is the prime. And now, since you are dealing with a PID, so irreducible elements and prime elements, they are essentially same. Okay, so for Z, it is very easy to find out all the maximal ideal. You just consider any prime ideal prime element P, okay, and consider the ideal generated by that. So these are the set of all maximal ideals of Z. So basically, the 2Z, 3Z, 5Z, 7Z, all are maximal ideals. We fixed a prime P, and then you consider the ideal generated by that. This is the maximal ideal. But if you are giving me arbitrary ring and you are asking me what are all maximal ideals, that is a difficult question. Even for polynomial ring, we can say something about the maximal ideals. Okay, when you have some geometric interpretation, in that case, yeah. So maximal ideal corresponds to the points. Okay, in ring of polynomials, what is maximal ideal? What do you mean by what is maximal ideal, or what are all maximal ideals for? No, what is maximal ideal? Huh.
Thank you, sir. Thank you for your response.
I think he was asking something.
Thank you, sir. Thank you for your response.
Okay, thank you.
There are so many relevant questions, but we are unable to take any further question as our time is limited.
Sure. If you have any query, just you can write me mail. But that's
okay. Thank you, sir. Thank you for your response. Thank you. I would like to introduce our second honorable speaker, Professor Adebayo Agunbade. Professor Agunbade is statistician and data analyst specialist. He parades 2 MSc degree in statistics and information science as well as a PhD in statistics from the University of Ibadan. He has put in some years of rigorous teaching and research at university levels. He has many articles in reputable journals and has co-authored some published books. He did some wonderful work on reputable projects like IEC project on women empowerment of a frontline NGO based in Ibadan, Nigeria. He is a reader in statistics at the Department of Mathematical Sciences, Olabisi Onabamji University, Nigeria. Now I earnestly request Professor Adebayo Agunbade for delivering his talk on most contemporary topic, recent advancement in mathematical sciences, a time series econometric approach to COVID-19. Viewers are free to ask any doubts or questions to speakers by typing them in the chat box on YouTube and Google Meet. During the session, the organizing committee members may ask their doubts or questions from respective speaker when their session ends. Please welcome Professor Adebayo Agunbade. Sir, you may proceed now.
Yeah. Good morning, everyone from Nigeria, and good afternoon to everybody in India. I'm happy to be back to my second country. Yeah, I have a lot of experience with Indian people, so it is my pleasure to also participate in the ongoing international webinar. Thank you, Madam Paul, for the kind introduction. Before long, I shall like to observe some protocol. Want to appreciate our patron-in-chief of the Chada College, our respected madam, for signing my invitation letter. And of course, I'm aware this program is a collaboration with MMT College. Want to also appreciate the patron. And of course, our guest, the chief guest, the representative of the government for West Bengal. It is my pleasure to be among you. More importantly, the HOD of Department of Mathematics, Professor Malik, who has been communicating with me over time. It is indeed my pleasure. I won't forget to also appreciate Professor Ghosh. Professor Kosi Ghosh is a treasurer of Calcutta Mathematical Society, CMS, of which I'm a live member. Where he approached me, I gave my consent, hence my being here today. So, I want to go ahead to share my presentation. Kindly be aware that I'm a statistician. The first person that gave his presentation is a mathematician, and of course, should expect some other parts of contribution from a statistician. Naturally, we are talking about recent advancements in mathematical sciences and its application. I want to refresh the memory of this gathering that we are talking about mathematical sciences particularly the current trend. We have majorly the mathematics, statistics, and computer science. Fortunately, I'm from the Department of Mathematical Sciences, where we award degrees in computer science, mathematics, and statistics. And as a professor of statistics, I'll be contributing from a time series econometric approach to COVID-19. Why COVID-19? We are talking about recent advancement in mathematics, sciences. So it's also good we let the gathering be aware that mathematical scientists have equally contributed a call for the use of vaccine and of course the non-pharmaceutical approach. So I will be showing the contribution of mathematician to approach of trying to also look for possibility of addressing the challenge of COVID-19 that is ravaging the whole world. So let me show my slide. Okay, please hold on. Give me a second.
Give you permission, yeah? Ask them for permission.
Yeah, I hope the organizer should give me permission to share my slide. Hello, Madam Paul, can you hear me?
Yes, sir. You are audible.
Please kindly give me permission to share my slide
Yes,
from your
yes,
hand.
of course. You can share your slide also.
Okay, yeah. I don't know, I'm having issues with the permission to share. I don't know.
Sir, any problem?
Yeah.
You
So the Google Meet.
under your screen, you see present now.
Yeah,
You
once
enter present now. Hello. Shahnaz. Shahnaz. হ্যালো শাহনাজ।
হ্যাঁ বলুন স্যার।
ওই পেজে শেয়ার করতে পারছেন, ওই প্রেজেন্ট নামে এন্টার স্ক্রিন করতে বলো।
সেটা তো উনি তো লেফটই করে গেলেন। আসুক বলা হচ্ছে আসুক।
তারপর ওটাকে মিনিমাইজ করে দিয়ে উনি যেটা দেখাবেন সেটা দেখাতে পারবেন।
হ্যাঁ 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 হ্যাঁ, উনি তো জানেন, আমাকে বলেছেন, আমি সব জানি। তো ঠিক আছে, আমি দেখছি, উনি আসুক।
আসুক। এমনি তো কথা বলতে পারে না, হোয়াটসঅ্যাপ ছাড়া ওদের তো বাইরের লাইন না, ফোনেও করতে পারবে না। আসুক।
ঠিক আছে ঠিক আছে। Hello, sir. Please unmute your microphone, sir. Please unmute your microphone. Agun Baide, sir. Please unmute your microphone, sir. Hello. Hello, Professor Agun Baide. Please unmute your microphone, sir. Please unmute your microphone, sir. Hello. Please unmute your microphone, sir.
I've done that. Can you hear me?
Yes, yes. Yes, sir.
Yeah.
You are audible.
Okay.
Please
okay.
go to screen and present now. Please, sir, go to screen, present now, and then go to enter screen, and then share. Yes, yes, sir. Okay, okay.
Yeah. Can you see it?
No, sir. No, sir. First, you present. First, click on present now, and then enter screen.
What about now?
Yes, sir. Yes, sir.
Yes,
Now.
now, okay.
Can you see it?
Yes, sir. It is audible. And sir,
Is it visible?
Oh,
Visible,
great.
sir.
Okay,
Visible.
yeah.
okay.
Sorry for
Sir.
that challenge. Yeah, I'm sorry. Yeah, that is my title page. The topic again, recent advancement in mathematical sciences, a time series econometric approach to COVID-19. Yeah, that is my university. To start with, I would like to give you the outline of my presentation. And first, I will be giving the introduction. I remember when the keynote speaker was talking, he gave us a lot of that trend, the development in mathematical sciences. It is not unlikely I will also be starting from that perspective so that the viewers and the whole world will indeed be able to appreciate the contribution of the mathematical scientists. And secondly, my second section intends to look at the current trend in mathematical sciences and their increasing significance. And of course, I would like to go into some literary review, trying to look at the mathematical sciences perspective to addressing the challenge of COVID-19. And of course, the next session, I would like to showcase some of the work that I did with some of my team, and want to share that. Particularly, the first case is a case of a cross-sectional survey that we conducted during the COVID-19 challenge. And of course, the results, of course, that are from Nigeria perspective. The second case was where we developed a mathematical model. We refer to it as INGAC mathematical model, and try to look at the daily cases of Nigeria infected person as revealed by the Nigeria Center for Disease Control in Nigeria. We modeled the data. The essence is to be able to have a representative modeling and then forecast for future cases of the infected person. This, we believe, will go a long way to be able to assist the government as to when the challenge of COVID-19, the curve of COVID-19 will be flattened, and of course, when truly the economy of the country could be fully open. And I will be doing that. Of course, I'll be giving my concluding remarks, some acknowledgement and references. Yeah, the introduction. Are you with me? Hello? Can you hear me?
Yes, sir. Yes, sir. You are audible.
Okay.
Yes, yes.
Yes, thank you so much. Oh, good. Thank you. Yeah, my introductory part is trying to showcase that our early mathematicians actually have a challenge of identifying who is actually a core mathematician. And of course, such development led to, particularly in my country and of course over the world, we have separately the contribution of mathematics, computing, statistics, and of course physics to the development in mathematical sciences. And of course, I bothered the technology to let us also know that this is a major advancement that mathematical scientists have been able to put into use. And you can imagine you are all back in India, I'm in Nigeria, and a host of other viewers from different parts of the world. I've been able to do that. I want you to be aware that that technology has the background of mathematical scientists. However, those trends, those development left out those areas that are not in the center of mathematics research today. You know, today the challenge is beyond just talking about mathematics, statistics, and physics. We are more of the applied. And of course, you remember we'll be talking about the machine learning, the artificial intelligence, biomathematics, and a host of other. In that regards, I shall also like to let's refresh our memory of those early contributors like the Pythagoreans. We are still using the Pythagorean theorem today. The John Napier, still talking about the logarithm, the Euler, the geometry, the Blaise Pascal, the Pascal triangle, of course, Leibniz, and from probability point of view, the Bayes, the Thomas Bayes, with their different contribution. And of course, the list is endless. You talk about Sir Isaac Newton, the Newton law, the Archimedes principle, and yes of other. I try to showcase the figure 1 here, trying to show the background where we are coming from as mathematicians. And of course, to average person, particularly from humanities, they wonder what's the jargon all about. But I should show you the trend. The current trend now, looking at separate departments or programs into mathematics, statistics, and computer science, and of course with branches into algebra, computing, functional analysis, artificial intelligence, machine learning, differential equations, calculus, topology, vis-a-vis a host of other data science, data mining. What is my interest? My interest is also just to look at give some literature review of some calculus-based mathematical models, some numerical analysis, fluid mechanics. More importantly, as statistician, we want to look at some Bayesian model and time series. And of course, from a computer perspective, you remember the deep learning, machine learning, natural language, and a host of others. The interest here is to showcase to us that the trend in mathematical sciences cannot be overemphasized, that the advancements actually now focus on mathematical competencies like problem solving, abstraction, mathematical formalism, and a host of other. Naturally, basic features of modern mathematicians are here. I would not want to waste our time on that, but however, it is also just to let us realize, if you look at virtually every faces of people that are participating as viewers or the eminent speakers here, you want to agree with me that the then mathematician, having seen them with their various features, is quite different from the trend of today. We want to talk about the simplicity of the current mathematicians or mathematical scientists. I mean, sorry to say, may want to liken it to the analog and the digital. The current trend now is about the digital mathematical scientists. Yeah, if we look at the figure 2, it's also showing the development, the trend in the development of mathematical sciences. Yeah, for this section, my interest here is to also showcase some applications of mathematical sciences to address the challenge of COVID-19. And here, my interest is to showcase 3 different perspectives. One, to let us realize that it is not just the use of vaccine and the non-pharmaceutical approach to COVID-19 that is possible, that we have various areas of applied mathematics are currently being used in modeling coronavirus in terms of the transmission, the detection of the virus, cause the forecasting, particularly using differential equations, using Bayesian time series model, using machine learning, and of course, artificial intelligence, and a host of other various areas of mathematical sciences. Yeah. I want to showcase to you the application from differential equation approach. Lemney and Taylor Hall developed a deterministic mathematical model for determining the transmission of COVID-19. And of course, in the course of that, the authors derived necessary conditions for the optimal control of the pandemic. And the model you have in equation 1 survives. The model was trying to look at the rate of the susceptible individual, represented by S, the exposed individual, the infected individual, and R by recovered individual, with the initial condition as in equation 2. We also have Magia 2020 that adopted the SIR model, and the author tried to calculate the basic reproduction number using next generation matrix method. Why am I showing some of this? Is to let us also realize that even when you're talking about the recent advancement in mathematical sciences, a host of such mathematicians, statisticians, and computer scientists have made such contribution. If you look at Charles et al. That adopted classical fixed point theory with the stability of Ulam's type by using the tools of nonlinear analysis to examine a population model of the novel coronavirus under approximate Bayesian computation fractional order derivatives. Aside from that, we also have such mathematical model using nonlinear ODE and of course with exact solution. And this was a case of modeling outbreak in Poland and Australia, respectively. You have a number of such authors. However, apart from mathematics perspective, here I also want to show us that the statisticians have equally contributed immensely. And I'm talking about the likes of Gagnon et al., who conducted Bayesian learning and forecasting for COVID-19 pandemic. The authors actually applied Bayesian sequential and adaptive dynamic estimation to surveillance to track and predict cases of COVID-19 with data obtained from Lombardia region in Italy and from USA. And that was at the peak of the virus. Yeah, you have a host of that. Yeah, let me also speak about we also have the time series model by Elazan and Gava. From the computer science perspective, we've been able to use machine learning and AI in the study by Pawara et al., Guzé, and Otok, and a host of others. Particularly, Tamuher and Mog apply machine learning, data visualization, and polynomial regression, and of course, support vector regression to predict the outbreak. And you know, the list is endless. But here, I will also now want to showcase the research conducted by my team. I want to show this gathering 2 cases. The case 1 was a study that was conducted to investigate the knowledge, attitude, and practices of Nigerians to the control of the spread of COVID-19. This research was actually conducted by my team, led by Dr. Peter Ogunyeka of my department, Dr. Dayo Adeleke of Obafemi Awolowo University, Ile-Ife, Mr. Banjo, and my Hebrew self. The interest here is to be able to determine that at what points should we advise the government, aside the use of vaccine and non-pharmaceutical approach, such that if we are able to know the knowledge, attitude, and practice of Nigeria during the lockdown, then you'll be able to know how best to be able to control the spread of the COVID-19. And of course, I'm going to share that result with you. Though currently, the outcome of such study was currently with the Springer Journal of Public Health under assessment. The case 2, when I was contacted by the team of the international webinar led by Professor Malik, the HOD, I had to contact one of my postdoc candidates, because of Dr. Lumide Additional of the Renewable Universities, and we agreed that we should look at the daily cases of infected person as recorded by the NCDC, Nigeria Center for Disease Control. And of course, we got the data, model it, and of course, went ahead to forecast for future cases and also have the trend of the graph, which also will assist the government of the country to be able to know at what point should the curve of the coronavirus be flattening. So the daily new cases of person that is positive to COVID-19 was actually classified as count data, and at the same time, in time series data. And so we developed an INGAC mathematical model in predicting for the next 20 years. The first case, just like I mentioned, was a case to determine the people's knowledge, attitude, and practice. And this was found to be highly significant to determine the sources as against the spread. We actually use semi-structured questionnaire as adopted from IFRC, that is the International Federation of the Red Cross and Red Crescent Society, and by UNICEF and World Health Organization. And this we are adopted and moderated by that team to suit the knowledge, attitude, and practice of COVID-19 in Nigeria. The questionnaire actually comprised a host of demographic section and the KP section. We have variables like state of residence within Nigeria, the gender, the age, the marital status of the respondents, the religion, the occupation, and the level of education. Our interest is to determine if the respondents actually know the transmission mode, know the symptoms of COVID-19, and of course the mode of
composed of molecular hydrogen, atomic hydrogen, and some traces of molecules. So that's why they are called the molecular clouds. So this is the picture of a molecular cloud. Often we call this as a nebula, and you see that there are some stars here and here. So the stars are found to be embedded in molecular clouds, and when there is no star, the molecular cloud looks dark. So from here, no stars have born. So this part is dark, but here some star is born. Here is star is born. So you can see this portion. So we can, from these observations, we can think that the stars are born out of this molecular cloud. So we have developed a theory that the molecular clouds, when they become gravitationally unstable, they collapse and they give rise to the formation of stars and star clusters. Now, this is the observation of a molecular cloud in different wavelength. Here the color is red. That means it is colder, rather colder. But here the color is green and yellow like this. So here the temperature is higher. So you see that some portion has a very high temperature, and some portion, and these are the different density contour. Here the density contour, it is the highest frequency. Here this is some lower frequency. This part has a still lower frequency. So you see that some portion, this portion has very dense structure, this portion has a very dense structure, but these are less dense portion of the molecular cloud. So from this we can have a theory scenario that the molecular clouds actually, they are the clumps of different densities. So which is a signature of the fragmentation of the molecular cloud. That is the molecular cloud. When they become gravitationally unstable, they collapse and they fragment. And each fragment, when they individually evolves, they give rise to a star. So this is the theory of the formation of stars in clusters. So when there are many such stars, the stars actually they form. If we plot the histogram of the masses of these stars, then it will give some curve, and that curve we call the initial mass function. That is the mass function of those stars which have born out of those molecular clouds. Now there are two types of star clusters. One is called the open clusters. They don't have any kind of structure. This is a picture of an open cluster. You see that the stars are spread and they don't have any kind of structure. And this is the picture of a globular cluster. And you see that the globular cluster has some spherical structure. But if we study these two types of clusters in greater detail, we see that these clusters are metal rich and they are young and they are metal poor and they are massive, they are metal poor, and they are older, and their age is comparable to the age of the galaxy, but they are younger than the age of the galaxy. So if we study, the globular clusters are very important. Why? Because if we study the formation of the globular clusters, then we can see how we can have some sort of information that how the host objects, that is the galaxy which contains the star clusters, how the galaxy has been formed and evolved. So the study of globular clusters, a large number of globular clusters in a particular galaxy, if you study their properties, you can have the history of the formation of the galaxy. Now, what is a galaxy? Galaxy is a gravitationally bound system. It is composed of stars and stellar remnants, and there is interstellar gas, dust, and poorly understood component which is called dark matter. That is the matter whose existence is felt by gravity, but the object you cannot see visually. That component is called a dark matter. Now there are different types of galaxy. So this is called the famous tuning fork diagram of the Hubble. Hubble is actually, he discovered the galaxies for the first time in 1920 when he was observing, and he nomenclatured these objects as the nebula. First, he didn't understand that these are the extragalactic things, that is the objects which do not belong to our galaxy. So these are the elliptical galaxy because they have elliptical shape, and this is the lenticular galaxy. They have some circular type of shape, and these are the spiral galaxy. The spiral galaxies has a typical structure that there are spiral arms. Every galaxy, the spiral galaxy, is composed of a disk, and you find the spiral arms in the disk, and here the stars are formed, and it is surrounded by a halo which is not visible. If you are to observe the halo, then you have to use a radio telescope, because in the halo there is hydrogen gas and which emits radiation, and the radiation has a very longer wavelength, that is the 21 centimeter, and that wavelength cannot be observed by an optical telescope. It can only be observed by a radio telescope, and the principle of the optical telescope and the radio telescope is very different. In the radio, the bandwidth is from radio wavelength, that is, it is of the order of centimeter or meter waves, whereas in the optical telescope, the wavelength is of the order of 10 to the power minus 8 centimeter. So there is a large difference between the wavelengths. So we compose different types of telescope for observing objects of which emit in different wavelengths. So this is the because we have only observations of electromagnetic waves from the universe, we cannot observe the thing without any telescope in great details. So this is, and there is another type of galaxy is called the dwarf galaxies. Our galaxy is a giant galaxy, and it is a spiral galaxy, and there are many dwarf galaxies. Dwarf galaxies are very small. For example, the mass of our galaxy is of the order of 10 to the power 11 solar mass, whereas the mass of a dwarf galaxy is of the order of 10 to the power 7 to 9 solar mass. So there is a difference in the mass. And another importance of the dwarf galaxy is that we have enunciated different theories of galaxy formation, and we have enunciated a theory that when numerous dwarf galaxies they collide, they will give rise to a giant galaxy. So if you study the dwarf galaxy in great detail, then you can also study the history of the universe, how the galaxies are. And this is the picture of our galaxy. It is the Milky Way galaxy. It's the central disk of our galaxy. And you see there are dark lanes because from here in the optical wavelength, when the stars, when the molecular clouds, they collapse, they only emit in infrared. So they are not visible in optical telescope, but this is an optical view. So it only gives you features when some light in the optical band is radiated. So from here, the stars have been formed, here no stars. So in this way, this is the picture of our Milky Way galaxy. Often we call our galaxy as the Milky Way galaxy. Now, what are the recent problems in astronomy, in astrophysics especially? We have seen that the molecular clouds are the sites of formation of stars. So, and when these molecular clouds, they become gravitationally unstable, they fragment, and each fragment, when individually evolved, they give rise to a particular star. So the stars of different masses. So the stars are of different masses. So if we plot the histogram of that is a frequency diagram. If we plot the frequency diagram of the masses of the stars, then we will get a curve. That is a curve. That is a distribution of the masses of the stars in the molecular clouds, and this is called the initial mass function. This study of this initial mass function is very important, because the question is that whether this initial mass function is universal, whether it has universal form in galaxy, in a particular galaxy, or it varies from galaxy to galaxy, or it varies in different molecular clouds. So as soon as there is variation in the initial mass function, there is variation in the characteristics of the spectrum of stars there. So the study of the initial mass function is very important in astronomy, because it will give you the clear picture that how the stars, how the system has been developed, has been formed, has been evolved. So this is one arena. Another arena is how galaxies are formed. The galaxy formation and evolution, this is also very, very important, because there are numerous galaxies and there are different types of galaxies. So how these galaxies are formed? So far we have very 4 or 5 theories, but there is no universal theory of galaxy formation. So there is dispute in the formation of galaxies. So what we do, sometimes what we do, we gather different properties of the galaxies, and then we statistically analyze, and we try to reach some conclusion from them. And on the other hand, we develop some mathematical theory, and we try to explain how this particular galaxy has been formed. So there are different approaches to know how the galaxies has been formed. So there are different theories, but no unique theory so far we have found for the formation of the galaxy. And you know that I have told you previously that the globular clusters, they are very important because their age is of the order of 10 to the power 9 year, and 10 to the power 9 year means giga year. So their ages are comparable to the age of the galaxy. So this is very important to study the globular clusters. So what is the motivation of the present work? The motivation of the present work is that we have tried to the scenario of the star formation theory in a molecular clouds. We observe the molecular clouds in galaxies, and if we develop some very convincing theory of star formation, that is over time, since a dynamical system give you the scenario of the time history. So if it is about the star formation scenario, then you will be getting the star formation history. So if you get the star formation history of a particular molecular cloud or a particular galaxy, then you can have all the information that how this galaxy has been formed, how the formation of stars in this galaxy. So I have tried to delineate some star formation theory in different categories of galaxy. Either it is a giant galaxy or it is a dwarf galaxy. So you can question me, why star formation? Star formation rate is it is the rate of formation of stars per year. Now galaxy is a big object. You cannot just count the number of stars because the age of the star is very long. It is very longer than your age. So you cannot study the number of stars. You just count the number of stars per year, and you cannot estimate in that way. So how do you estimate this? So there is no true value of the star formation rate. What we can estimate, that we estimate the flux in different bands, whether it is in hydrogen, or it is far ultraviolet, or it is infrared. So different bands we count the flux, and we integrate over all the wavelengths of that particular range, and it is called the integrated flux, and we assume that this integrated flux is a measure, is an estimate of the true star formation rate. Okay, and we have seen that if we estimate the star formation rate in different galaxies, then it is different for different galaxy. For example, in dwarf galaxy it is low, in giant galaxy the star formation rate is high, like that. So in the present model, we have developed a model of the star formation. Now, what is a molecular cloud? In a molecular cloud, the central part is of highest temperature, so it contains the hot gas. Then this hot gas is surrounded by a warmer portion. This is called the cold gas, and then it is further surrounded by a colder component. This is called the cold component. And a star cannot form in a hot gas. Star always can be formed in a cold gas, because if the gas is not cold, then the gas cannot collapse gravitationally, because during the collapse, if heat is generated and if heat is trapped, then at some time the thermal pressure will just stop the gravitational pressure. So you have to overcome the thermal pressure. And what is the way out? Way out, that is the heat which is generated during the collapse should pass out from the object. Then the collapse can continue. So presence of cold gas is very important, and you know that in the initial collapse stage, the density of the molecular clouds is so low that heat just passes away from the molecular cloud, and molecular cloud just collapse. And this type of collapse is called the isothermal. Why isothermal? Because the temperature is more or less constant. If the temperature is more or less constant, and if the temperature is low, then only the collapse can continue. And when the density of the molecular cloud is very high, then the heat is trapped and the collapse stops. So the molecular clouds should be very cold, and actually the stars are formed in these cold components, not in these hot components. So we have taken three components, and these are the fractional abundance, that is the cold component of the molecular cloud. This is the warm component of the molecular cloud, and this is the hot component of the molecular cloud. Then how these components varies over time. This is the component. This is the sweeping of warm gas into the cold component. That is, warm gas, when they sweep, this is, and this particular, this is the constant. It denotes the rate at which the warm gas just sweeps to the cold gas. Now this is the evaporation of the cold cloud embedded in hot gas. Actually, this picture is a very cartoon picture. In molecular clouds, we have several such condensation here, like. So sometimes it may happen there is a cold part which is just beside the hot part. So this is the rate of the evaporation of the hot cloud into the cold cloud. And why this is a square term? Because the radiation, the radiative cooling is lower than the exponential cooling. Because if you take all these things are constant, then this is no longer an exponential change. This is slow, rather slow than exponential. So this is slow, that's why the power 2 has come. And since this is the warm component is deposited on the cold component, so there is a deficit of warm component, so it is accompanied with this. And also what is this part? This is the cooling of hot gas in warm gas. Cooling of hot gas in warm gas. And this is the rate of the flow of the hot gas into the cold gas. That is, cold gas, if it has a very high velocity, then it can come to the cold portion. So these are the different physics, the different types of physics which are associated with the evaluation. And this is a conservative system, because this cold component, warm component, and the hot component, this is equal to 1. We have dimensionalized by the total mass of the cloud, and these are the fractional component, and the fractional component, they together give rise to a value 1. That is xc, xw, and xh equal to 1. Now in astronomy, what we do, that if there is a variation in the dimension, suppose this is a quantity which is very small, it has been observed, it is of the order of 10 to the power minus 6, and this is not so. So how do we compare these things together? So what is we do? We make all the quantities dimensionless, and we take the dimension of this part is equal to the dimension of that part. So how do we dimensionalize, make it is dimensionless? We take tau as the dimensionless quantity of the time, and we divide tau by t, tau by c, and we get the time. And we make also dimensionless capital A, B, and F introduced by dividing the constant c to A. So these are comparable. These are now comparable constants. And these are now comparable constant, and these are the fractional component. Now, since it is a conservative system, we can eliminate any one equation. So we have eliminated the one part, and we have taken only the cold and hot part. Why? Because the stars actually are formed in the cold part, and there is a law of the Smith law, that is the star formation rate is proportional to the cold component. Some power of the cold power, 1.4 like that. So it is star formation rate mainly depends on this cold component. So we are interested in the equation which involves the cold component, and we rename the variables at xc as x and xh as y. Now we should solve this two first order nonlinear differential equation So what is the method of solution? First, we make the left-hand side 0 and we find the different values of x and y, which are called the stationary points. Now what we do? Now, what are the stationary points? Now, about stationary, in the neighborhood of the stationary points, the fluid is in equilibrium. Now, we like to study the stability of this stationary clouds. So why we like to study the stability? Because suppose there is a molecular cloud and there are different sectors in a molecular cloud, and which are the stationary points. Now, if the fluid comes closer and closer in time to the point, then there is a possibility of the formation of stars, because if the cloud is gravitationally unstable, then what happens? Then the fluid becomes of higher density at the center. That is, the fluid actually flows to the center. So first of all, we find the stationary point, so that we make these terms equal to 0 and we solve the equations. So we have got here 4 stationary points. Now in the first, you see that x equal to 1, that is, the cloud is only composed of 4 components. But in practice, there is no cloud which is only consists of the cold components. So it is not a physically acceptable solution. So we the mathematicians only do solution. We don't care about whether it is, but we the physicists always have to consider the physical things. That is, whether the solution is physically acceptable. If it is not, then we should not consider that solution. So from physical point of view, this we can take, because y equal to 0 is not possible in any molecular cloud. Then for solution 2, there are 2 values of x and y, which depends on the constants a, f, etc. And for the third and fourth solution, also these are extreme situation. The stationary, if you just add this quantity, they give you value 0, that is x plus y equal to 1 in your case. So x plus y equal to 1 means xw equal to 0, and that is also not physically acceptable. So the one component, because in every molecular cloud there are different components, hot, warm, cold, 3 components are there. So this is also, they are not physically acceptable. So what is the physically acceptable? So number 2 solution is the physically acceptable solution. That is x plus y plus z equal to 1. Not all the components are 0. So we are interested in the solution 3. This is only the realistic solution. Now what we do, we have studied the stability condition. So what we do, we just a minute. We just plot the cold component, and we psi is the star formation rate, and psi bar is the average star formation rate. So we have normalized this, and if we normalize this and we take different values of the parameters, now when we study the stability condition, what we do? In the original equation, it is a set of 2 nonlinear first order differential equations. So what we do, we give a small perturbation to the variables. Here the variables are x and y. So we give a small perturbation, x plus x0, y plus y0. Okay, and this variation we take as an exponential form. Exponential form what? E to the power lambda t type, where lambda is some parameters. So we substitute those x plus x0 and y plus y0 in the original equation, and we ultimately get an equation in lambda. So that lambda, if you solve the value of lambda, it will be actually the eigenvalues of the Jacobian matrix. So if this lambda is negative, then there is stability. if lambda is positive, then there is unstable position. So the stationary points are not stable, then they are unstable. So in this way, we study the stability analysis. So here we have plotted the star formation rate, which is actually proportional to the cold component of the molecular cloud for different values of the parameters. And if we see the different values of the parameters, here there is a parameter B. What is the B? B is actually evaporation of hot gas in the cold gas. When stars formed in a molecular clouds, what happened? The stars evolve, and the stars form also supernova. So when the supernova, they undergo explosion. You know that what is supernova? Supernova is a big star. When it explodes, then it is called a supernova. So when such explosion occurs, then what happens? This hot gas, it flows with a high speed. Okay, so the hot gas is actually is thrown into the cold cloud, and the hot gas gets evaporated. So when the value of B is very large, so it means that the rate of supernova explosion is very high. But when this value of B is low, then the supernova explosion is rate of supernova explosion is low. So we know that in giant galaxy the supernova is very high, and dwarf galaxy supernova rate of explosion is low. So we can identify these parameters as the parameters for giant galaxy, and this is the parameter for the dwarf galaxy. So in this way we can see that various features. You see that here the star formation rate about the stationary point 2, that actually falls very rapidly compared to the dwarf galaxy. This is a very zoom portion of these two figures. So in giant galaxy, the star formation rate falls rapidly, but in dwarf galaxies, the star formation rate undergo cycle, that is oscillatory model. That is, the star formation is very high at some time, then it goes very slow and stops, and then again it is high, then again it is low, and it continues for a very longer time, because it takes time. These are the same time, but it is a very rapid, and this is longer. So we can study in this way the different outcomes of the star formation rate in different galaxy. And this is some pictures of the corresponding, and for some values of the parameters there are limit cycles. What are limit cycles? These are the if suppose it is a stationary point, you suppose this is the coordinates of x and y of the stationary points, some points. Now you take some solution at somewhat larger distance, and if the movement is along this direction and some lower distance, again it drives to this point, then this is called the stationary points. That is, there is no decay of the star formation rate, but the star formation rate remains constant over all period. That is called that is the physical analog with the stable center of the star formation rate. Okay, now we have done another thing of the differential equation. We have also we have studied the time evolution of the different elemental abundance. That is, in galaxy we see different elements, and with the component of the there are gaseous component in a galaxy, and there are I stands for the different metals. The metals are generally iron, oxygen, etc. So these are the equations. These are the different terms, because it depends. The formation of the metals actually depends on the star formation rate, then the instantaneous return fraction of the stars in the molecular cloud, and formation of the new stars, then infall from the galactic halo, So all these factors and the outflow from the galaxy. So different physical phenomena are associated with these mathematical terms. So if we all include in the evolution, time evolution of the metal evolution of this galaxy, then what we get? We also get different features for giant and dwarf galaxy. The thing is that in giant galaxy, you see that the metal is very higher value. They maintain that this is the observed value and this is the predicted value. These are, hello? Hello? Can you hear me? Hello, can you hear me?
Yes, ma'am. You are audible.
You see, you see that in giant galaxy the metal has very high value, and the metal has the value over 0. But in dwarf galaxy, you see that metal has very lower value, and this actually tallies with the observation. So in dwarf galaxy, the metal abundance is lower than the giant galaxy, and we have matched our predicted result with the observed one. So these are the different phenomena we can observe from the if we make a very successful model. So these are the different results for the stable points. And what is the future direction? Our future direction is that this can be here we have taken a conservative system. Conservative system means there is no gas, there is no escape of gas from the galaxy. And in the dynamical model, the system was conservative. But in the dynamical system, if we consider the outflow, here the outflow we have considered a different set of differential equations. Why? Because the time scale. Because the time scale of the second equation is much larger than the time scale of the first set of differential equation. In the first state, the time scale is of the order of 10 to the power 7 years, while in the second situation, the time scale is of the order of 10 to the power 9 years. So if we cannot introduce those terms into the first equation, so we have constituted a different set of differential equations for the second set to study primarily the abundance of the different elements like iron, oxygen, etc. That because those abundances also gives you importance, it clues to the scenario for the different galaxies. So that's why we have studied those. But there are also systems where the outflow is of the order of the oscillating episodic model, episodic time. So there we can introduce the outflow. That is, we can consider the open system. First, we have considered in the first system, my system was conservative. So not only conservative, we can also consider the open system, that is non-conservative system also. This can be used to study the chaos under the influence of supermassive black hole Saturn, and we know that in every giant spiral galaxy, there is at the center there is a black hole. So if we, in addition to these things, we can also introduce the black hole things, but then we have to consider the equations of the general theory of relativity. We cannot use the use of ordinary classical things, but that can be done. And this system can be used to study the formation and stability of single and double bar and bar. In spiral galaxy, there is at the center of spiral galaxies there is a bar. For example, our spiral galaxy, there is a single bar, but in some galaxies there are double bars. That is, there are 4 stable points at the end of those bars. So how these stable points have been formed? So we have to study. We can constitute a mathematical model for that. and this can be used at the origin of formation of single and binary stars, because when a star cluster is formed out of the molecular clouds, the stars can form as a single star, and the stars can be formed in binary stars. The stars can be formed in multiple systems also, because 3-4 stars, they combine together and they form stellar association. So how these systems are formed under different parametric situation, we can constitute a model with the help of dynamical system, and this can be used for dissipative system, as I told you earlier. So these are the future directions of these dynamical models, how the dynamical models can be used in different astrophysical aspects. So this is the end of my talk, and I suppose I have consumed my time also. So if you have any question, I am ready to answer you.
Okay, ma'am. Hello. I think I am audible.
Yeah, you are audible. You are audible.
Okay, ma'am. I thank Dr. Tonuka Chattopadhyay wholeheartedly for her presentation. Now we would like to take questions from audiences. First question have come up from
How do we have?
The question is, after death, what our sun will become?
After death, our sun will be a white dwarf. And when the initially the white dwarf, because now it is the age of a sun is of the order of 10 to the power 10. So now it is 4.5 billion years, and it will be another 5 billion years. The sun will survive, and after when all the metals are exhausted at the center of the sun, then it will end its life as a white dwarf. Initially, you will be able to see the white dwarf because of the high temperature at the surface of the white dwarf. But gradually, when it radiates, it will become cold, and it will be a black dwarf. You cannot see the object, and you can only have its. You can feel the objects by its gravity, but with a optical telescope you cannot see the sun. And there is also another story that in the mean life, the sun will be a red giant. When it will be a red giant, then it will engulf all the planets, including ours also, and that will be the end of the solar system.
Thank you, ma'am. Thank you for your response. We are unable to take any further question.
What is a pulsar? Pulsar is actually if the star is very massive. Suppose the star has some mass from 2 to 3 solar masses. Then what will happen? First, it will be a white dwarf. But because if it is of greater mass than the white dwarf, then the core part will still contract. So what will happen? The electrons will combine with the protons, and they will form neutrons. And there will be some electrons in the outer envelope of the stars to maintain a stable structure of a neutron star. And when the neutron star will further collapse, then the magnetic field will increase. Then it will be a rotating neutron star. That rotating neutron star is called a pulsar.
Thank you, ma'am. Thank you for your response. Now we are unable to take any further questions as your time is limited. I again thank Dr. Tonuka Chattopadhyay wholeheartedly for her presentation.
And I have one request, that they are asking for my sharing my email ID, so that if they have many questions in their mind, so you can share my email IDs. I am giving you permission.
Okay, ma'am. Okay, ma'am. Thank you. Now I would like to introduce our honorable speaker, Dr. Satyabachi Shor. Dr. Shor retired as head of the Department of Mathematics of MBB College, Agartala, Tripura in 2004. He was guest faculty of mathematics at Tripura University and served as professor of mathematics in Techno India College of Technology, Kolkata. Besides teaching research, he has been engaged in popularization of mathematical sciences in various capacities. He has written extensively both in Bengali and English. So far as he has authored 11 books, more than 200 articles, including 60 research papers. He has been honored and facilitated by several renowned organizations. I would like to request him to deliver his talk on Ramanujan and a glimpse to his work. Viewers are free to ask any doubt or questions to speaker by typing them in chat box on YouTube and Google Meet during the session. The organizing committee members may ask their doubts or questions from respective speaker when their session ends. Dr. Shor, you may proceed now.
Hello, can you hear me? Hello.
Yes, sir. You are audible now. You can start your presentation.
Good afternoon, everyone. At the outset, I must thank the organizer for inviting me to deliver a lecture on this special occasion. I have chosen the topic Ramanujan and glimpse of his work for two reasons. First one is to pay homage to I chose for two reasons. First one is to pay homage to our national pride and mathematical hero, Ramanujan, on 100th year of his immature passing away, and second one is about the rich mathematical heritage of India, coming beyond London. Both life and a glimpse of work of
Sir, can you put your mic little bit closer to your mouth? Can you put your mic little bit closer because sound is very little bit closer to your mouth. The mic.
Can you hear me now? Hello?
Can you put the mic a little bit closer to your mouth?
I'm not audible.
Yes,
now?
yes, yes. It is now visible. It is now audible. It is now audible.
Okay. So, presentation of this Ramanujan and a glimpse to his work due to two reasons. First reason, to pay homage to the national hero and mathematical hero of India, Ramanujan, on 100th year of his premature passing away, and second is to create awareness among the young learners about the rich mathematical heritage of India. Now, topic is Ramanujan and glimpses of his work. Srinivas Ramanujan, G.H. Turnbull, in his book, The Man of Mathematics, said, just by absolute standard of greatness among all mathematicians of the East, the genius Ramanujan appears to be the supreme. On April 22nd, 1941, Professor H. Neville started his speech on the All India Radio with the sentence, Srinivas Ramanujan was a mathematician so great that his name transcends Jailers, the one superlatively great mathematician whom India has produced in the last 1,000 years. Professor J.H. Hari, in Harvard Centenary celebration in 1936, said, I have to form myself as I have never really formed before and try to help you to form some of the reasoned estimate of most romantic figure in the recent history of mathematics, a man whose career seems full of paradoxes and contradiction, who defies almost all canons by which we are to judge one another, and about whom all of us will probably agree in one judgment that he was, some sense, a very great mathematician. Really, Ramanujan is one of the greatest mathematicians of all time. Srinivas Ramanujan was a man of incomparable intellect, unbelievable merit, unparalleled insight. He lived a very short span of life, but his mathematical work is of about 2 decades, would dazzle East and West alike for centuries. His work will have an everlasting effect in the history of mathematics. He added a new dimension to the whole world of science. Professor Ken Ono of Emory University rightly said, Ramanujan was really a poet, not a problem solver. He was someone who could set down the paths or beginnings of important theories, and really so. Freeman Dyson said, Ramanujan discovered so much, yet she left so much in his garden for other people to discover. Those who have come directly or indirectly in his contact in any manner must come under his wondrous spell. His life was a rags to intellectual riches story. Part of it might be lifted almost unchanged by a senior writer for topics, এবং it is indeed to mention that few talkies have been created on life of Ramanujan. One of them is The Man Who Knew Infinity, which was released in 2015, 15 September. Now, defining moments of Ramanujan life. Ramanujan life was just, I said, can be lifted unchanged, almost unchanged for talkies. His life was really enthralling. Now, in short, just I am giving, it can take at least 2 hours to describe in details. Now, just I am giving the defining moments of his life. Just mentioning this, Ramanujan was the eldest son of Kuppuswamy Srinivas Iyengar and Komalata Mall. His birthday was 22nd December. He was born in 1887, and he was the eldest son of, and his birthday is celebrated in India now as National Mathematics Day. On 26th December 2011, celebrating the 125th birthday of Ramanujan, Prime Minister of India, Dr. Manmohan Singh, then Prime Minister of India, just declared on the behalf of the Government of India National Mathematics Day, and since then we are celebrating this. And Ramanujan's education start at age of 5. And in 1997, he was first in the primary examination in the Tanjore district and got admission to the Kumbakoram Town High School. And at Town High School, he stood fast. At Town High School, he studied from 1898 to 1903. Here, he impressed his classmates, senior students, and teachers by his extraordinary skill, aptitude, intuition, proficiency in mathematics. The first recognition of Ramanujan's remarkable mathematical gift can be treated when he received K. Ranganath Rao Prize at the annual prize distribution ceremony of his school held in 1903. And 1903 is a very important year in the life of Ramanujan. And it is a turning point of his life when he got a book, a synopsis of elementary results of mathematics written by G.S. Carr. And Ramanujan was this book influenced Ramanujan immensely. Ramanujan, what is there in the book? There is almost 5,000 theory, formula and theorem, for most part without proofs. Ramanujan set to work systematically to establish this result. And in proving one formula, he discovered many others and began to compile his famous notebooks in the line of synopsis. In college, Ramanujan devoted himself more and more to mathematics and neglected other subjects. The result was inevitable. He could not pass in English, and hence he was not promoted to senior FA class. He lost his scholarship. A very trying period of his life began. However, in 1906, he got admission in another college, Pachayappa College in Madras, in FA class. But he fell ill. At last, he had to discontinue his study. Now, he appeared privately in FA examination, but failed. Now, gradually, after his failure, he has to work under extreme hardship, but preserve his mathematics and continue his research work. His research marched undented by any environmental factor, physical, economic, social. Ramanujan continued his work, developed mathematical ideas, and began to pose problems and solve problems in Journal of Indian Mathematical Society. His first research paper appeared. His first research paper was on Bangali numbers, appeared in 1911 in January in the Journal of the Indian Mathematical Society. Gradually, his mathematical works came to the notice of the person like Ramaswamy Iyer, founder of Indian Mathematical Society, Ramchandra Rao, Dayan Bahadur of Nerol district, P.V. Sheshiwar, professor of Madras Presidency College, once teacher of Ramanujan. Now, in 1910, Ramanujan, meanwhile, in 1909, to draw the attention of Ramanujan to the family affairs, marriage with Janaki Ammal was arranged by his parents, and Ramanujan was frantically in search of a job. He has nothing but notebook. He has no FA degree, only notebook. He first met Ramaswamy Iyer, then later he met, on advice of Ramaswamy Iyer. Ramaswamy Iyer was the founder secretary of Indian Mathematical Society. And then he, with the advice of the Sesu Ayar, he made Ramchandra Rao. Now, with the help of these people, he made application to the post trust, and at last he got job in the post trust, and he joined March 1 on. Now, in 1936, and with the advice of O.L. Sir, Ramanujan wrote a letter to Gottfried Harold Hardy, FRS, and Fellow of Trinity College. And this letter was one of the most important and exciting letters ever written. No one who was in mathematical circle in Cambridge at that time can forget the sensation caused by this letter. This letter, filled with about 120 mathematical theories, later identifies to be startling. Ramanujan Hardy received a large untidy envelope decorated with Indian stamp, which was filled with wild, fantastic looking theorem and formulas. At the first glance, Hardy was not impressed at all. So Hardy left it aside and got himself in the daily routine. In the evening, Hardy again started examining the theorem sent by Ramanujan with the help of his illustrious colleague, J.E. Littlewood. And the more they looked, the more dazzled they became. And before midnight, they knew for certain the writer of the manuscript was a man of genius. Hardy would rank Ramanujan's letter as certainly the most remarkable letter ever received. Hardy understood for full flourish of untutored genius Ramanujan, arrangements should be made for arrival in Cambridge as early as possible. However, with Hardy's initiation and involvement of many people, University of Madras did grant Ramanujan a scholarship of £2,050 per annum for 2 years to maintain him in Cambridge and his family in Kumbanam starting from April 1, 1914. And Ramanujan sailed for England on March 17, 1914 by the ship SS Neva. At last long, Ramanujan came to the right place, to the right people. Right people means Hardy. And for 3 years, alone and in collaboration with Hardy, Ramanujan produced mathematical papers of the highest quality. In rapid succession, then he fell ill seriously. He had to spend quite a lot of time
Excuse me, sir.
at different nursing home
Hello.
and sanatorium.
Excuse me, sir.
Ramanujan stayed in England for 5
Sorry
years
for interruption.
and prepared
Excuse me, sir.
21 wonderful research.
Dear
Among which
Julius,
5 years
dear
in
Julius,
collaboration with
please,
Hardy.
please
All in
stop
all,
your
in
video.
his entire career, he had 37 papers, of which several were
Dear-
jointly Hardy.
Excuse me, sir.
Many honors.
Excuse me, Shuddhabati, sir.
Yes. Yes. What?
Dear
Yes.
Julius, please. Dear Julius, please stop your video.
Yes. Yes, I'm listening.
Sorry for interruption, sir. Dear Julius, please stop your video. Okay, sir. You may continue.
Should I continue? Hello?
Hello, sir.
Hello.
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 Hello, Shruttabaji, sir.
Should I continue? Yes.
Yes, sir. Yes, sir.
I am listening.
Sir, you can continue and put your mic little bit closer
Should
to
I
your mouth.
continue?
Yes, sir. Yes, sir. You can continue.
For Ramanujan in England. In March 1916, he obtained BA degree from Cambridge University for his research paper on highly composite number. And in 1917, he was elected as a member of London Mathematical Society and fellow of Cambridge Philosophical Society. And February 18, he was elected fellow of the Royal Society, and October 10, he was elected as fellow of Trinity College. And Ramanujan was the first person, first Indian to have these two honors at simultaneously. And in the meantime, from 1907, Ramanujan fell ill and he had to spend in sanatorium and nursing home for a few years. And after receiving the honors, his health improved, and it was thought that the honors which bestowed on Ramanujan acted on him positively, and it seemed that he improved bodily and mentally. Ramanujan sent to India for further improvement of his health under familiar climatic condition of matter. And Ramanujan sailed to India on February 17, 1990, and reached at Bombay port March 27. But in India, his health did not improve at all. In spite of every care was lavished, best possible medical facilities were provided. He died on April 26, 1920. Now, these are few famous photos of Ramanujan. This photo is well-known photo of Ramanujan, and when Professor Hari are preparing, publishing Ramanujan collected papers, he needed a photo of Ramanujan, but he had none. He asked S. Chandrasekharan, the Nobel laureate, to arrange for one. And S. Chandrasekharan came to India and met Janaki, Ramanujan's wife, and collected from the negative, from the photo of his passport when he was returning from England to India. This photo was prepared. Now this is next photo is another photo in the Western dress and Western haircut, and this photo is a photo in front, taken in front of the Senate House. Now, Ramanujan's works at a glance. Ramanujan works can be found in the collected papers of Srinivas Ramanujan. It was edited by G.H. Hari, P.V. Sesu Iyer, and B.M. Wilson. It contains 37 papers by Ramanujan during his lifetime and 58 questions, some of which is defined parts, and 5 solutions sent by him and published in the Journal of Indian Mathematical Society, 2 biographies, one by Ramchandra Rao and Sesu Iyer, another by G.H. Hari as the obituary notice in London Mathematical Society, notes on paper, abstract of Ramanujan's letter to J.H. Hari. The third reprint contains additional commentary by Bruce C. Burt. Now, notebook. He wrote 3 volumes of notebooks with 3,254 results, whose photocopies were published in 2 volumes by TIFR in 1957. Bruce C. Burt edited notebook in 5 parts in an effort of 20 years with the cooperation of other mathematicians. And it is a treasure for the mathematics, Ramanujan's notebook. It has a long history how Ramanujan's notebook was edited. First, Ramanujan brought his notebook to England, and in June 1912, 2 papers were prepared from his notebook and presented by Hari in the London Mathematical Society. Then Hari feared the edition of Ramanujan's notebook, and with the initiation of Madras University, G.M. Wilson, B.M. Watson and Wilson, they started editing. Prematurely passed away B.M. Wilson in 1935. Then it was left, and at last Bruce C. Burt started editing in 1977 and completed in 1998. Lost notebook of Ramanujan. Now, we are just, I quote Robert Canningall, who is the writer of the invaluable book on the life of Ramanujan, The Man Who Didn't Fifty. Can we understand Ramanujan's life without some appreciation for mathematics that he lived for and loved? Which is to say, can we understand an artist without gaining feel for his art? Now, a few words on highly composite number, which was published in the Proceedings of London Mathematical Society in 1915, and for which he was awarded BA degree from Cambridge University. Now, what is a highly composite number? A natural number is defined to be a highly composite number if its number of divisors exceeds that of its predecessor. We know that 1 has only 1 factor, 2 has 2 divisors or 2 factors. So, first highly composite number will be 2, and in this way, the first 15 highly composite numbers are 2, 4, 6, 12, 24, 36, 48, etc. I have written over here. And this is the longest paper of Ramanujan, consisting of 63 pages and 269 mathematical relations. Hari said about this paper to be the most remarkable. He remarked that there is no question to the extraordinary insight and ingenuity Ramanujan had shown in treating it, and that it showed very clearly Ramanujan's extraordinary mastery over the algebra of inequalities. Ramanujan has no method. Ramanujan wrote, there was no method of determining consecutive highly composite number except trying. But in his paper, Ramanujan gives a list of 102 consecutive high composite number and the corresponding value of Dn. Dn means divisor of n. and also DDN. DDN means divisor of DN. In the list, some highly composite numbers in the table are marked with asterisk signs, and these are later defined as the superior highly composite number. For this massive calculation, Ramanujan took only very short period of time. What a stupendous and exceptional computational ability. However, one thing to be noted here that somehow Ramanujan missed the 90th highly composite number, namely 293,318,625,600, and which can be factorized this way, which has 5,000, 50,000, 5,000 40 divisor. The omission was pointed out by T. Vijayaraghavan, who was the first director of the Ramanujan Institute, built in 1957 in memory of Ramanujan. And this was this. And the last number, that is 1,000, our highly composite number is this 63. Just you can see from my presentation, and its DN is this, and it is its DN is the 20th highly composite number. Now, Ramanujan had 7 joint papers with Hari, and out of these 7 joint papers, 2 was most important in the history of mathematics, and one is asymptotic formula in the combinatorial analysis. It was the second largest paper of Ramanujan, consisting of 41 pages. This is celebrated joint paper. Ramanujan and Hari made significant progress in the determination of an asymptotic formula for Pn. Pn means the number of partition of the integer n, that is the number of ways of divisor of n into positive integral parts. For example, we can express 3 is equal to 3, 2 plus 1, 1 plus 1 plus 1 in 3 ways. So Pn is equal to 3. In this paper, they proved, Ramanujan and Hari proved, Pn is asymptotically equivalent to this expression as n tends to infinity. This is one of the most remarkable results in the theory of numbers. Equally remarkable was their proof. In the commentary on the papers of Ramanujan, Bruce Bond said, it is very important paper, Hari and into what is now called the circle method. Since the most important tool in the additive number theory, it had many applications. It has been applied in the particle physics. And one of the most remarkable applications of Ramanujan and Hari as a problem deals with problems of particle physics. The theory of partition of numbers has found to be very useful for study of Bose-Einstein condensation of the perfect gas. The central problem is determining of the number of ways given amount to energy can be shared among different possible states of the thermodynamic assembly. This problem is essentially the same as the finding number of partition of number into integers under certain distribution. And Littlewood said, we owe to the theorem to a single rooted the best, most characteristic and most fortunate work that was in him. Ramanujan's genius did have this one opportunity worthy of it. Hungarian-born Cambridge mathematician Béla Bollabás remarked, I believe Hari was not the only mathematician who could have done it. Probably Mordell could have done it. Polya could have done it. I am sure there are quite a few people who could have played Hari's role. But Ramanujan's role, in particular partnership, I think cannot be played by any other else. Now we come to the normal number of the prime factors of n appear in the quarterly Journal of Mathematics in 1917. Hardy and Ramanujan in this paper explored the properties of the round numbers by discussing systematically the number of prime factors of integers. One of the fundamental results they showed in the paper was that almost all integers n have log n prime factors. Roughly speaking, round number are those which have substantially more prime factors. Composite number between 991 and 100 have an average of 4 prime factors, but 1000 it is 2 to the power 6 into 5 to the power 6 has 12 prime factors and hence turns out to be very round. One commented this paper without doubt one of the most and this is what is most interesting. This paper was the instrumental for the emergence of the probability number theory. Paul Hofmann observed it is testimony to the power of the great mathematics that such diverse subjects, prime number theory and probability theory are linked. Now, I come to the very well-known episode of Ramanujan. Perhaps almost all people know this episode, and we know that Ramanujan was very fond of numbers and very fond of numbers raised to the power, especially power third order. And this is this episode shows his extraordinary brilliance and memory. I am telling this episode in England when Ramanujan was ill and lying in sick bed of a nursing home at Putney. Professor Hari had come to see him riding taxi cab bearing number 1729. Arriving near Ramanujan, he uttered the number and remarked, "The number seemed to be rather dull one, and that I hope it is not an unfavorable omen. Indeed, 1729 is the product of 3 prime numbers, 7, 13, 19. But just listening to this, Ramanujan's face glittered, and he replied, "No, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways. In fact, 1729 is 10 cube plus 9 cube and 12 cube plus 1 cube." Then and then, Hari inquired if Ramanujan knew the corresponding number of the 4th power, that is, the least positive integer, which can be expressed as a sum of 2 4th powers in 2 different ways. Ramanujan thought just a while and answered, "It must be a big one. Actually, the number is a natural number of the 9 digits, and it is 635318657, which is expressible as 158 to the power 4 plus 59 to the power 4, or 133 to the power 4 plus 334 to the power 4. Incidentally, this number was discovered by Leonhard Euler. Here, one may note that the least number as mentioned by Ramanujan means least positive integer. The 2 cubes mean cubes of 2 positive integers, not of 2 other kind of integers. If they denote the not positive integers but simply integers, we would have the required least positive integer expressible as 2 cubes in 2 different ways as 91 instead of 1729, because 91 is 6 cube plus minus 5 to the power 3 cube, 4 cube plus 3 cube. However, what is most remarkable of this episode regarding Ramanujan's exceptional power of memory and of recapitulation of the relation among numbers is that there is no explicit mention of the number 1729 in any of his notebook or any question sent to the Journal of Mathematics. However, a relation equivalent to 10 cube plus 9 cube is equal to 12 cube 2 can be found in few places. The places are there. Question number 661, Indian Journal of Indian Mathematical Society, Volume 7, page 119. This is solve in integers, this, and deduce the following. And here in the default ink, it has been given. Next, numbers raised to the power, question number 681. Here, solve in integer this and deduce this. Here we can find this. Also, in Ramanujan notebook, there is a theorem which states that if alpha square plus alpha beta plus beta square is equal to 3 lambda gamma square, prove that alpha plus lambda square gamma whole cube plus lambda beta plus gamma whole cube is equal to lambda alpha plus gamma whole cube plus beta plus lambda square gamma whole cube. It is interesting to observe that if we put alpha is equal to 3, beta is equal to 0, gamma is equal to 1, lambda is equal to 3, the relation becomes this. Now, presently, the natural number expressible as a sum of two cubes of two positive integers in two different ways is termed as a Ramanujan's number. We give a few examples of this kind of numbers. Here, I give the first 5 such Ramanujan numbers. I just written over here. I am not just mentioning it. The time is short. You can please see it. And now, that Ramanujan was found relation of numbers of different power can be established by going through his notebooks. One can find many such examples in notebook. To give here only a selected one below, just a sample subject. Now, can I ask how much time I am available for me? Hello? Should I continue? Approximation, now I start.
Sir,
Approximation
you
of
have-
irrational number.
Sir, you have only 5 minutes left.
Only 5 minutes left. I started well. All right. I shall try to finish it within 10 minutes. Approximation of a irrational number by rational number. Here I am going to mention a situation with which many mathematicians were familiar, but only Ramanujan could observe its potentiality and exploited it to yield a very interesting and beautiful result. We know that successive terms of the Fibonacci sequence are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. And the sequence is defined x1 plus x2 is equal to 1 and xn is equal to xn by 2 plus xn minus 1 for n is equal to 2. It has been known since centuries that the newly formed sequence xn by xn by n constructed from the terms of Fibonacci sequence, that is sequence 1 by 1, 1 by 2, 2 by 3, 3 by 5, 5 by 8, 8 by 13, 13 by 21, etc., is convergent and converges to the limit minus 1 plus root over 5 whole divided by 2. And this limit is positive root of the quadratic equation. 1 is equal to x plus x square. And Ramanujan has a brilliant idea to reverse the whole procedure. He thought that if we had the equation 1a1 plus x plus a2 plus x square, where a1, x are these things, then and a sequence xn be formed in this way, then question arises, would it be true that the sequence would converge to the root of the equation 1? He found that it was indeed true. Thus, a method of approximation of the irrational number by rational number was found found out by him. In fact, he went much further. Ramanujan stated, if x is such satisfied this equation too, then the sequence this, x1 is this, x2 is this, xn is this, then the sequence will tend to x as x tends to infinity. Interesting enough, he used this theorem to get an approximation of log 2. Let us see how. We know that if log 2 is 2, then e to the power x is 2. And this implies this thing. E to the power x means 1 plus x plus factorial by x square by factorial 2x cube by factorial 3, etc. Now this is equal to this, and comparing 2 and 3, we are getting a1 is equal to 1, a2 is equal to 1 by 2, a3 is equal to 1 by 3, 1 by 6, a4 is equal to 1 by 24, a5 is equal to 1 by 120. Hence, the term of this sequence are given by this, and so we are getting this. Thus, the term of this sequence are given by 1, 1 by 3 by 2, 3 by 2 by 13 by 6, 13 by 6 by 25 by 8, 25 by 8 by 551 by 120, etc. And this is this. And the claim is that the sequence tends to log 2 as n tends to infinity. Indeed, the fourth convergent, fifth convergent, 1, 2, 3, 4, 5, fifth convergent is 0.6931608, where log 2 is this. This is really an astonishing achievement, exploiting the known result, just immutable result. Now, I just give the source of insight of Ramanujan. He posed this beautiful question, what is the value, find the value of root over 1 plus 2 root over 1 plus 3 root over 1 plus 4 root over, etc., etc. And he found it to be 3. And how he found it? Here, this is the solution. And next, this is also an very important, very illuminating problem. Now, this all about my presentation, and just lastly, I'm going to present one thing. So this is a magic square. This magic square is because I'm going to show the magic square of Ramanujan's birthday. Now, can you see it? Hello?
Yes, sir, visible.
Yes. Now,
Yes, sir. This is
and his magic square, Srinivas Ramanujan and his magic square. This square looks like any other normal magic square, but this is formed by the great mathematician of our country, Srinivas Ramanujan. And just we see the sum of the rows is 139. Sum of the column 139. the sum of the diagonals 139, sum of the corner 139, and the sum of the blue marked places 139, and the blue marked places and red marked places 139, and the center 4 places 139, and the 4 contour 139. And this is also another combination. It is also 139. Now let's come to the climax. The birthday of Ramanujan is 22nd. We all of us know that 22nd December 1887. And this is the Ramanujan magic square, and would be a proud man. And now which I told earlier, now this magic square, if anyone can copy this and with their birthday, they can form this magic square, form magic square of their birthday of any person. D, date, month, A means month, year, 4-digit number. The first 2 digits is C and last 2 digits is Y. Now in the second row, Y plus 1, C plus 1, M plus 3. So from this, one can form the magic square for birthday of any person. So thank you. This all about it. And this is references. And one thing, you please go through the references. There is reference number C7. Mathematical Wizard Ramanujan and His Legacy. It is written by me, and recently it has been published by Bigyan Prasad. And this book is available. Those are interested to receive this book, you can contact bigyanprasad.gov.in. Here is this. And also, I wrote another book in English, Gonit Jagoter Vishoy, Ramanujan, published by Gyan Vichitra. It was first published in 2006, and its third edition has been printed in 2020 with much modification. And these are the very invaluable book of Ramanujan, G.H. Hari Seswayar, collected papers, Bussy Bont and Rankin, Ramanujan Session Survey, Robert Canningal, the beautiful and most charming book on Ramanujan's life, G.H. Hari, 12th lecture, which is inspiration to many, Deep Universe Now, and Ramanujan's letter and commentary. I have taken from all these references all the information. Thank you very much.
Thank you, sir. I thank Dr. Shatyabachi Shor wholeheartedly for his presentation over Ramanujan's work in mathematics. We are unable to take any question as our time is limited. At the end of the today's session, I modestly request our convener, Dr. Shahanush Malik, present HOD and present Assistant Professor of Department of Mathematics of Chakda College to give vote of thanks.
Hello.
Yes, sir, you are audible.
Please stop the sharing mode of Dr. Shor. Please stop your sharing. Dr. Shor, please stop your sharing. Thank you, Momita. Good afternoon, everybody. I am Shahanush Malik, Assistant Professor, Department of Mathematics, Chakda College. It is my privilege to have been asked to propose a vote of thanks on day one of this international webinar. Recent advancements in mathematical sciences and its applications. On behalf of the Department of Mathematics, Chakda College, and organizing committee of the webinar, I extend a sincere thanks to the honorable speakers, teachers, and participants who blessed us with their virtual presence and took out valuable time of their busy schedule. I must mention our deep sense of gratitude to Professor Adebayo Agunbaide, Professor Tanuka Chattopadhyay, Dr. Shatyabachi Shor, and Dr. Muhammad Ali Jinnah for enlightening us with their wonderful lectures. I hope that these lectures will help us and guide us in the future. I want to express our sincere gratitude to the Honorable Chief Guest, Dr. Partho Kormokar, Deputy Secretary, Academic, West Bengal Board of Secondary Education, who has spared his precious time for us and graced this webinar with his presence. I would like to extend a special thanks to Ashok Kumar Das, Principal, Ashannagar MMT College, for inspiring us to the webinar. I am very grateful to our Principal Madam, Dr. Swagata Das Mohanto, for giving us an opportunity to organize this webinar and her continuous encouragements and supports. I must mention our deep sense of appreciation to Dr. Anirban Banerjee, Assistant Professor in Zoology, Chakda College, for his advice regarding web communication of the webinar. Also, I like to thank Mr. Onif Rai for his technical advice and supports. Finally, I wish to express my earnest thanks to our departmental colleagues, Dr. Nitya Gopal Bishwas, Sri Bishwarup Chattopadhyay, Ms. Songjukta Pramanik, Ms. Momita Pal, Sri Sonod Ghosh, Ms. Mampi Majhi, Sri Rakesh Rai, and Sri Kaushik Das for their continuous efforts towards the betterment of the webinar. As no program can become successful with a single person, so I extend my big thanks to all our teaching and non-teaching staff of Chakda College for making today's event successful. Besides, I would like to thank all the audience for their presence and attention throughout the day one of the webinar. Thank you all again. Have a nice day. Thank you.
I thank our convener, Dr. Shahanaz Mogli. Now we are concluding our webinar and shall definitely meet tomorrow according to our scheduled time. Till then, take care yourself and thank you.
Momita, please tell about tomorrow. Momita, please tell about tomorrow's program.
Sir, today feedback is required. Hello. Sir, can you tell about the feedback?
Feedback will be available after end of the webinar.
Okay, sir. Thank you so much, sir.